Hi guys, I am Neeraj Toshniwal. I am currently studying in IIT Bombay, doing my BTech in Computer Science. I secured AIR 21 in IIT JEE 2009 and was also a gold medalist in National Chemistry Olympiad. So, as far as inorganic chemistry is concerned, we are done with S block elements. So, today let's move on to the next important block of the periodic table, that is P block elements. So, S block covers from group 1 to group 2 and P block elements covers group 13 to group 18 of the periodic table. So before starting the periodic table, before starting the P block elements, I was just like to give an mere introduction what we are going to study in P block elements. So P block elements, as I have told you, covers group 13 to group 18, and each group has been assigned a different properties, has different properties. So we will study the properties of each group one by one and proceed in that way. So as you know that P block elements has an electronic configuration of ns2 np126. The p orbital can have 1 electron to 6 electron. Based on this, the group number is decided. In the periodic properties, I have told you that the group number of P block elements is decided as 10 plus number of electrons present in the nth valence orbital of P block element, in the nth valence electrons. That is, if you want to determine the group number of boron, that is the 1s2, 2s2, 2p1, so it has a valence electrons 2 plus 1 3, so its group number would be 10 plus 3, that is 13, and subsequently the group number of other elements is also determined. So let's start with the first group, that is group 13, the boron family. So before starting the boron family, I will just write its elements. Group 13, that is Bal Jayanti, that is boron, aluminium, gallium, indium and thallium. So as we go down the group, it's not that important. So it's not that important. Thallium and indium, very less property we are going to study. Most of the properties we are going to study of boron and aluminium as far as group 13 elements are concerned. So first, general properties of group 13. So starting with it, first would be the atomic radii. So we know that as we go down the group, atomic radii increases. However, in this case, the atomic radii of gallium is quite similar to that of aluminium because of poor shielding of 3d electrons. Because of that, the radius of aluminium is nearby equal to radius of aluminium, and in the indium and thallium, the radius of indium in fact is greater than the radius of thallium, because very poor shielding effects by the 4f and 5f electrons, because by 5f electrons, therefore radius of thallium is less than as compared to radius of indium. However, we are going down the group. So that's the order of the radius for group 13. Now considering the ionization energy also has the very, I should say, exceptional order, because whenever we are talking about the ionization energy of group 13 element, we are talking about the sum of first three ionization energy, because we are interested in only the cationic form of B plus 3 or aluminium plus 3, because most of the compounds which they form exist in their trivalent oxidation state, trivalent ion state. So if you are talking about the sum of first three ionization energy, then boron has the maximum ionization energy, but in aluminium and gallium, again because of that poor shielding effect, the sum of the ionization energy of gallium is greater than the sum of ionization energy for the aluminium, and same follows for indium and thallium also. However, the difference here is larger and difference here is less minimal, but between these two, again the sum of the ionization energy for gallium is greater than the sum of ionization energy of indium. So it is quite an exceptional order as far as the ionization energy and atomic radii is concerned. So you have to keep in mind, because these have been asked in the previous year JEE exams about these things in the JEE also, in NCERT also, and CBSE board also, and in AIEEE also, and other board examination. This is quite a common question about their comparing the atomic radii or their ionization energy. Now the next would be the electronegativity. We know that down the group the electronegativity decreases. However, we don't study about the electronegativity of aluminium, gallium or indium or thallium or even boron, because these are more or less metallic in character. All are metallic in character, and boron shows an anomalous property and it is non-metal. So we don't talk about the electronegativity of a metal. Generally we just talk about the electronegativity of a non-metal, but as far as the electronegativity trend is concerned, it decreases generally down the group. The next property next would be the physical property. As I told you, boron is the only element of group 13 which is non-metal in character. As we go down the group, the non-metallic character decreases, or in fact aluminium is a metallic, rest all are the metals. Aluminium however shows some property that are analogous to that of the boron. However, gallium, indium and thallium are quite metallic in nature. Considering about the oxidation state, so there are two, as you know, the electronic configuration for group 13 would be ns2 np1. So there are two valence electrons in the s orbital and one valence electron in the p orbital. So as we go down, we encounter +1 and +3 oxidation state in group 13 elements. So as we go down the group, the screening constant or the shielding constant for the s orbital electron on the valence electron of s orbital decreases quite frequently. So the effective nuclear charge increases. So as we go down the group, the +1 oxidation, the stability of +1 oxidation state increases and the stability of +3 oxidation state decreases. So boron, aluminium and gallium are mostly found in the +1, +3 oxidation state. However, indium and thallium are more stable in +1 oxidation state because of poor shielding effect of F and D electrons, and because of that the effective nuclear charge on s electrons increases. They do not participate in bonding, these s electrons do not participate in bonding, and therefore their +1 oxidation state is more stable for indium and thallium. This is also known as inert pair effect. Because of increased nuclear charge, the valence electrons cannot participate in bonding. It is also known as inert pair effect. Now talking about their covalent bonding, so they always, if they form the bonds by sharing, so you can say that they will always form the there will only be 6 valence electrons, so they are electron deficient, so they can act as a Lewis acid. I told you earlier that Lewis acid is that one that accepts the electrons. So it is an electron deficient species. All the compounds of these group will be electron deficient if we are following the octet rule. Therefore it can act as a, it has vacant orbital, so it can vacant p orbital, so it can act as a you can say Lewis acid. However, in this case boron, it doesn't have the vacant d orbital, because in the when the value of principal quantum number is 2, there is no d orbital, so its maximum covalence is only 4. It can only form 4 bonds. Boron can only form 4 bonds. However, as far as aluminium, gallium and other group 13 elements are concerned, they have the vacant d orbitals, and therefore their covalence can be exceed 4. In fact, it is 6 in most of the cases. Their maximum covalence is 6. Now talking about the reactivity towards air, so they react readily with air and form their corresponding oxide. B2O3, as we know, is not a Al2O3, we know as this is a amphoteric in nature. However, and they also reacts with nitrogen. Boron reacts with nitrogen and form Bn, that is BnX, and it is also known as inorganic benzene. Because the structure quite resembles to that of a benzene, therefore it is also known as inorganic benzene. So reaction of boron would be with nitrogen would be this, and it will form a Bn. So if you want to just so it would be 2 boron plus nitrogen giving Bn, and its structure, its polymeric structure would be something like boron, nitrogen, boron, here nitrogen, so it would be a 6-membered ring which is quite similar to that of a benzene, and this is shared, this nitrogen is again shared, and this is continued in the same way in all the 4 directions. So it is something like this structure which extends in all direction. So therefore it is known as the inorganic benzene, and here nitrogen gives its lone pair to the boron, because boron has the vacant 2b orbital and nitrogen has a lone pair, and it donates it to here, and or I should say it donates it to here, and it donates it to here. So this is how, and the same is also followed in each ring. So it is something like this, that is overall dispersion of that lone pair, and therefore it resembles to that of an benzene. However, this is more reactive than benzene because it has two different atoms participated in this inorganic benzene, boron and nitrogen, difference in electronegativities. Therefore it is more reactive than benzene. In benzene there is also only the carbon in this ring, so therefore it is less reactive than this is inorganic benzene, or you can also call boron nitride. Now reactivity towards acids and alkalis is concerned. So as I told you earlier, the aluminium is somewhat amphoteric in nature. It reacts with acids also and it reacts with bases also. So AlOH whole thrice, which is the product when it reacts with acid, it is predominantly basic in nature. However, it also shows the acidic characters sometime. So more predominantly it is basic, but it also shows acidic character. Yeah. So next one would be the trends and important trends and anomalous property of boron. So as we have studied in S block elements also, that lithium and beryllium diverge from the properties of other elements of their respective groups. The same follows for boron also. This is mainly because of the absence of vacant 2d orbitals, and therefore its maximum covalence is 4, and because of its small size and greater electronegativity as compared to the other elements, it has some anomalous property. Okay, so now we come to the individual. We will study boron and aluminium individually, and we will first start with boron. So boron is found in nature in many compounds, in many minerals, namely borax, coleonamite, but mainly it is found in two. One is borax, that is borax would be borax, that is Na2B4O7 10H2, and the other would be boric acid. So these two are the main compounds from which in which boron is found, boric acid and borax. These two are the main compounds. So as far as the preparation of boron is concerned, it is prepared from potassium tetrafluoroborate, that is KF4. When it is KF4 is reacted with the potassium and heated simultaneously, it forms 4 molecules of KBF4, that is potassium borofluorate, that it forms 4 KF and also forms the boron this. So this KF is then removed from the solution by reacting it with HCl and forms HF and KCl, and then subsequently it is removed, and what we get is boron. Yeah, so now we will study the properties. Boron is a very crystalline structure, and unusually crystalline structure and very hard structure. So its reaction with air and oxygen and about the nitrogen, I have told you earlier that it reacts with nitrogen and form inorganic benzene, that is BN, which is more reactive than benzene, and also it reacts with oxygen to form B2O3. As far as the reaction with alkalis and acids is concerned, so it reacts with acids and alkalis both and form their corresponding acid. For example, if the reaction with H2SO4 is concerned, then boron reacts with H2SO4 and form its corresponding acid, that is boric acid H3BO3, and so it is a, you can say, redox reaction, because boron from 0 oxidation state has been oxidized to plus 3 oxidation state, and subsequently SO2 is released. So it is a redox reaction, and you can, I think, balance it quite easily, because it is just change of electrons, transfer of electrons from one compound to other compound. So it is a redox reaction. Same happens with HNO3 also. H3BO3 is formed separately with the elimination of NO2 gas. Now consider its reaction with the alkaline earth metal, namely magnesium and calcium. So it reacts with magnesium, forms Mg3B2 and Ca3B2. Let's say Mg reacts with boron and forms Mg3b2. So this is, again you can say it is a redox reaction. Here the boron is showing the negative oxidation state and Mg is showing the +2 oxidation state, boron is showing the -3 oxidation state. So it will be 3 Mg and 2 boron giving Mg3b2. Now Mg3b2 same happens with calcium also. So Mg3b2 again reacts with the, if you do its hydrolysis, that is if you add its hydrolysis in the acidic medium, that is HCl, for time being hydrolysis, then it forms diborane, that is B2H6, which I have told you has 3 center 2 electron bond, banana bond so to say, and MgCl2 also. MgCl2 is formed, so it would be 3 MgCl2 and boron would be B2H6. So this would be the reaction, and B2H6 further on hydrolysis gives S3BO3, that is if addition of H2O here, it gives S3BO3. So this is again boric acid, or also orthoboric acid is it's also. This is how the Mg3b2, its reaction with this reaction is important because some reaction have been asked on the hydrolysis, what happens when the hydrolysis of this is done or something. So diborane hydrolysis gives the boric acid, and the hydrolysis of Mg3b2 would give you diborane. So this was the reaction, and again if you will take in extractive metallurgy, boron is produced by the Van Erkel method, that is 2Bi3, which is borium iodide 2Bi3, when it is heated or in the presence of red hot tungsten, which can act as a catalyst, which is red hot tungsten, it forms boron plus iodine. Iodine is separated and boron. So this is also known as Van Erkel method. You will learn more about it in extractive metallurgy, Van Erkel method for the preparation of boron. It is used in the extractive metallurgy. So yeah. Next would be, now that was all about the reactions of boron, its reactivity towards air and water, about acids and alkalis. Now we will study the important compounds of boron, and first would be the B2O3, that is boron trioxide. So its preparation is quite I should say unusual, that S3BO3, that is boric acid so it is, we are studying about B2O3, that is boron trioxide. So S3BO3, when it is heated to 100 degrees centigrade, it loses one water molecule so to say, and it forms HBO2, which again heated to 160 degree forms H2B4O7, which is, you can say, the diprotic acid of Na2 borax, that is Na2B4O7, and which again on heating, that is heating, gives us B2O3. So this is how the boron trioxide is prepared, and this reaction is important as far as J is concerned, because this is quite an anomalous behavior, because depending on the temperature the preparation is done. So just it is an important reaction as far as all the exams are concerned, the preparation of B2O3. Now this was about B2O3. B2O3, as you know, is acidic in nature, but it can also show weakly. So it is it has a weakly basic property, that B2O3 reacts with P2O5. Predominantly it is acidic in nature, as you can say. It is an anhydride of boric acid, anhydrous of boric acid, so it is predominantly acidic in nature, but with some bases, with some acids, you can say very high acids, it can show the basic character also, that is B2O3 reacts with P2O5 and forms 2BPO4. So this is the reaction. This is here it acts as a base, here it acts as an acid. This is how it's defined. So this is the reaction of this. So base and acid, and so predominantly it is acidic in nature. So this was all about the boric acid or boron trioxide, sorry. So B2O3 important, this reaction is quite important, that on 100 degrees centigrade it gives HBO2, which on 160 gives H2B4O7, and which again on heating will give you boron trioxide. So next compound, and the most important compound of boron, would be the orthoboric acid, that is, or simply boric acid, that is S3BO3. H3BO3, that is orthoboric acid. So orthoboric acid is a monobasic Lewis acid, so to say. It is a Lewis acid, that is, it is not a proton donor acid. Mostly acid, if you talk about H2SO4, if you talk about HNO3, all these acids, when they are dissolved in the water, that is, if they are dissolved in water, they releases H plus. They release H plus, and consequently anion is formed. So because of this H plus release, they are known as the protic acid or proton donor acid. However, with S3BO3, this is not the case. S3BO3, we know that the boron here has one vacant 2p orbital. So when it is dissolved in water H2, the OH minus ions of this attacks here. So it would be something like BOH4 minus. So it would be something like this, and corresponding to it, the H3O plus would be formed, H3O plus aqueous in the aqueous form. So because of this, it acts as a acid, but however it is a Lewis acid. You can say Lewis basic, Lewis acid. It is not a proton donor acid, and it is only a monobasic acid, because after the acceptance of one OH minus ions in it, it has no more vacant 2p orbital, and therefore it only acts as a Lewis monobasic acid. So very important reaction, and very many questions have been asked on this acid, orthoboric acid, on the properties of orthoboric acid. Because of this happens, so you can just you can say balance the equation. Yeah, so this is again, but you can here say that BOH3 you cannot use it in titration because it reacts partially with water and it acts as a very big acid. Therefore you cannot act as a titration and just predict its pKa values or something like that, because therefore, but if we add some other compound, that is, let's say if I add here some sugar, or then it acts as a very strong acid, and when if we titrate it with NaOH, then we can have rough idea about its pKa values, because when we add it sugar and other organic compounds which have cis-2-diol, I should probably say cis-2-diol is added, then this reaction, then this BHOH4 minus is consumed, it is consumed in second reaction, and because of this reaction will go in forward direction according to concept of ionic equilibrium. This, since the product is constitutively removed, therefore this reaction will go in forward direction, and therefore it will act as a more you can say strong acid as far as weak acid is concerned. So generally it is a weak acid, but however if cis-2-diol is present in the solution, that it behaves as a strong acid, and its titration can be done with NaOH in that case. So what happens with cis-2-diol is something like that. It forms a compound which is stable compound, and that's why the reaction goes in forward direction. That is H3BO3, that is BOH whole thrice you can write as something like that. It reacts with NaOH, that is used for the titration of boric acid. So it forms NaBOH4 and plus NaBO2 plus 2H2O. Now this BOH4, this reacts with the cis-2-diol, that is twice of, you can say, COH here, OH here, so it will be CH2. So this is cis-2-diol. It reacts with this and forms boron here and oxygen, something we call something like this, and here CH, here CH, here it is here, and here it is CH, here it is CH. So it forms a compound like this, and consequently to it H plus is released. So this compound is constantly used in this reaction. So because of this simultaneous reaction, product is being consumed, so this reaction will go in forward direction, and therefore it acts as a, you can say, a strong acid in presence of cis-2-diol or something like that. However, if trans-2-diol is present, that is in trans-2-diol, this would be in the opposite direction, OH, it's stoichiometry, then it will not, this compound will not form, and therefore this will not go in the forward direction, something like this, trans to diol. It is not clear here how this will happen. So trans to diol is concerned, it will not go in forward direction, this reaction will not take place, and it will act again as a weak acid. So because of cis to diol, it acts as a strong acid. So this is an important one. Simultaneous to cis to diol, there is also, you can say, salicylic acid. Salicylic acid is has a structure of benzene, and it has a hydroxy group at ortho position of carboxylic acid. So this is also known as salicylic acid. Salicylic acid. So this, in presence of this also, it will go in forward direction because it has these two oxygen, and these two oxygen can donate to boron, and the H plus will be removed. And catechol also will act as, it is simply the OH here, OH here, it is also known as catechol. So these are both the organic compounds, salicylic acid and catechol, and the same reaction will happen if we use, in place of cis to diol, we use catechol or salicylic acid. It will again act as a strong acid. So this was the reaction, and this was the behavior of orthoboric acid in presence of the diols, or I should say cis to diol. Cis is very important. If it is trans, the reaction will not happen as we have predicted. So H3PO3, as you can say, has an oxygen and hydrogen. So in crystalline structure, it is very you can say compact structure and hydrogen bonded structure. So its structure would be something like this, that it has boron here, oxygen here, and I should yeah. So here it is interaction here it is interaction here, and here it is something like this. So this is one unit of orthoboric acid, would be something like this. So it has hydrogen bonding with the other elements also. It is hydrogen bonded to here, this is hydrogen bonded to here, and this is hydrogen bonded to here. So if I draw another one unit of, this is oxygen, this is boron, this is again oxygen, this is oxygen. So this oxygen is, this is of this oxygen, and here it is something like this. So this forms a 6-membered ring, I should say. There are hexahedral layer. I have shown only 2 molecules, but overall there are 6 molecules, and because of that it is very hydrogen bonded, very structural hydrogen bonded, and therefore it forms a layers, and there is a crystal. But and the layers are quite far distance apart, that is 3.18 angstroms from apart. The layers form the 3D structure in, you can say. So these two layers are bonded by van der Waals forces, and which are quite apart. So when you break it, the crystal breaks structure into very fine particles. Now as far as the test for borate radical is concerned, that is, so for the test of borate radical we use the ethyl alcohol or C2H5OH. That is, when the H3PO3 is added more, you can say C2H5OH, then C2H5OH, this oxygen attacks the vacant 2p orbital of boron and forms and replaces other OH and forms BOC2H5 whole thrice. This is the product formed, and something 3H2O. So this compound, that is boron ethyl borate, is a very volatile structure and is burnt using green flame. So this is the test for the borate ion, because it runs the green flame. So if on adding the C2H5OH green flame is produced, then we can definitely confirm that it has a boric acid. You will learn more about this test in inorganic salt analysis. Next important structure of this would be the borax. Borax of the boron acid would be borax. So let's head it to borax. So I have told you earlier, the formula or molecular formula for borax is Na2B4O7.10H2. That is Na2B4O7.10H2O. However, the correct formula for, or I should say the correct geometry of the boron, this borax would be something like Na2B4O5 OH4 dot 8H2O. This would be the correct formula for the borax, that is Na2B4O5 OH4 dot 8H2O. It is a coordination compound, as you can see, and it has a charge, this anion has a charge of -2. Yeah. So the first question would be the properties of borax would be that borax on heating, when you heat borax, that is Na2B4O7 dot 10H2O, on heating loses all its water of crystallization and forms Na2B4O7 plus 10H2O, that it loses all its water of crystallization, but it is only up to the heating to certain extent. However, if it is heated further and if the temperature reaches 720 degrees centigrade, then you can say borax bead is formed, that is 2NaBO2 plus B2O3. It is also known as borax bead. Borax bead is formed, which is used in the test for many cations. So on heating to 720 degrees centigrade, if it is less than 720 degrees centigrade, then it loses all its water of crystallization. But once the temperature reaches the 720 degrees centigrade, it decomposes into NaBO2 and B2O3, that is boron trioxide, and forms a borax bead of this. Yeah. So oxidation of boric acid, as I have told you, that NaBO2 is formed, and when this NaBO2 is further reacted with H2O2, then it forms again the boric acid, that is H3BO3. So it is again an important reaction, sorry, not H3BO3, it forms another compound, that is Na2. Na2 would be here, and OH whole twice would be here, and here would be B, in middle it would be state. So I will draw the structure, complete structure for how this is formed. So it's 2 and it is OH whole twice here also. So this structure is formed in this, not boric acid, so it's my bad, I told you boric acid. So this structure is formed, and this is something, it is cyclic structure. It would be something like, here it is boron again, so it would be B O O B O O B, it would be something like this, and here one OH, and other OH would be the coordinate or dative bond, and other would be this is minus, this is minus would be here. If you will try to replace it plus and minus, it will be. So this is the whole structure for this anion. So this was the structure. Important reaction, I should say, because it's these type of reactions have been asked frequently in the competitive exams, when its behavior is different when it is heated to up to certain amount, up to certain temperature, and its reaction is different if it is heated up to above that temperature. So this would be the reaction, this is the compound, important reaction for the borax. Yeah. So next would be this, I am talking about this. This has the 5 BOB linkages. Its structure is very important because it has been asked. So if it has 5 BOB linkages, 2 boron have the trigonal planar structure, 2 boron have the tetrahedral structure. So important, if you want to talk about some important properties of borax, one would be it has 5 BOB linkages. It has 2 different type of boron, I should say, because 2 borons are tetrahedral in shape and 2 borons are trigonal planar in shape. So this was about the borax, and next would be the borax bead test. Just tell you a little bit about the borax bead test, which is used for it forms color, the cation forms colored beads with the borax bead. So when it is heated to 720 degrees centigrade, it forms B2O3, which is glassy, and reaction of this B2O3 with transition elements, so to say, if you react it with, let's say, Cu, it forms CuBO2 whole twice, which is a blue bead. So color, it forms colored beads. So color would be different for other transition elements also. So in fact this is used for the inorganic salt analysis. For the borax bead test is very important for transition element, differentiating transition elements. So Ni plus 2, Co plus 2, Cr plus 3 all forms color beads, and their colors are all different. So borax bead test is very important as far as the inorganic salt analysis and differentiating the cations from other cations is concerned. So this is the borax bead test. So next important compound of boron, boron would be the B2H6 or diborane. I have talked much about diborane in the chemical bonding part also, that it has 3 center 2 electron bond, very different structure, or very, I should say, unique structure from the rest of this. B2H6 would be diborane. So boron forms two types of, or I should, two families are there. General formula BN HN plus 4, and one is BN HN plus 6. Here N can take values starting from 2, here N should take values starting from 4 and increment. So these are the two families. I talked to you about the B2H6. B2H6 structure would be something like this. It is a 3 center 2 electron bond, B2H6, B2H6 diborane. This is a 2 center 3 electron bond. So 3 center 2 electron bond, its bond length is greater than this BH because only 2 electrons are there. They are oscillating over between this boron and this boron. So very important properties of diborane. So some of the reaction or the preparation of diborane would be, it forms is with the BF3 is when reacted with LiAlH4, Li plus AlH4 minus ion, then B2H6 is formed. So this is one of the important reaction how to prepare diborane. Here B2H6 is formed. So depending on this reactivities, the B2H6 when reacted with amines forms cleavages of certain cleavages are done in this diborane structure. That is B2H6 when reacts with amines, so to say, let's say if I write here X, it forms H2B2 X2 H2B2 X2 or H2, yeah, H2B2 X2 plus BH4 minus. So unsymmetrical cleavage of the B2H6 is done, and something like this is produced. Here X would be small amines and ammonia also. Ammonia and small amines. So if B2H6 react with NH3, it would form H2B NH3 whole twice plus and BH4 minus. This is an unsymmetric cleavage of B2H6. However, here by small amines I would mean primary and secondary amines, but the in case if it is X is a large amine, then for example I will take the NCH3 whole as a trimethyl amine, then it forms a symmetrical cleavage and it forms 2BH3, and to boron the NCH3 whole thrice is donating. So if the amine is larger, then it would have the symmetrical cleavage. If the amine is smaller, or it would be ammonia. Ammonia is not a amine, by the way, it is a different amine. So it will also give the unsymmetrical cleavage. Very important property, depends on this also. Now B2H6 is when react with ammonia, it forms, depending on the condition, it shows different properties. Let's say first I will take, there are 3 conditions on which the products are depending. Let's say B2H6 when reacts with ammonia, where the ammonia is in excess, and low temperature is used, low temperature is there, then it forms B2H6 dot 2NH3 is formed, or for the betterment I should say the reaction which we have studied right now, that is H2B2NH3 whole twice plus BH4 minus. This is what is formed if there is, it is in excess and it is in low temperature. However, excess NH3 is used but the temperature is greater than 200 degrees centigrade. The NH3 is in excess but the temperature greater than, it forms inorganic benzene, or BNX is found. Inorganic benzene, I told about you, is structure also known as the boron nitride. and if it is not in excess, the ratio of NH3 to B2H6 is 2:1, and the temperature is less than 200 degrees centigrade. If the temperature is less than 200 degrees centigrade, if the temperature is greater than 200 degrees centigrade and the ratio is 2:1, then borazine is formed, that is B3N3H6, also known as borazine. It again has a structure resembling to that of benzene. Structure of B3N3H6 would be boron, nitrogen, boron, nitrogen, boron, nitrogen here. This will be donating here, this will be donating here, and this will be donating here, and hydrogen to each. Again, this will be more reactive than benzene because of the same reason, because the electronegativity of the elements in the ring is different, so more reactive towards the all the reaction or addition reaction, or what you can say. For example, if you say it shows some addition reactions that is not shown by the benzene, this shows that it is more reactive than that of a benzene. So it was B3N3H6. So this was all about the properties of boron and important compounds of boron. Let's move on to the next element of the group 13 family, that is aluminium. Aluminium is a white solid, as I told you earlier also, and it is amphoteric in nature. It has some properties similar to that of boron, but it is again amphoteric in nature. It is a metal. Aluminium forms an oxide Al2O3 when reacts it with oxygen, which is amphoteric in nature. It also reacts with nitrogen and form aluminium nitride, and AlOH whole thrice is formed if on hydrolysis of aluminium AHOL whole thrice is formed, which is a precipitate, I should say, not dissolved, completely dissolved. It is sparingly soluble and it forms a white precipitate. So this aluminium, the reduction of it acts as a reducing agent in one or two reactions, that if MnO2 is reacted with aluminium, then it forms the Al2O3, oxidizes itself and reduces the manganese. Same happens with the ferric oxide also. If you react aluminium with Fe2O3, then Al2O3 is formed and ferrous ion would be released. So these are the important reactions. Here the aluminium acts as a reducing agent, and this is based on the reactivity metal series. You will learn about it in extractive metallurgy. If the element here is less reactive as far as that reactivity series is concerned, then it will replace here the element from here and forms an oxide. However, if the metal used here is above in the chemical reactivity, then aluminium will not be able to replace this metal from this oxide. So this was about the oxidations. So now considering the Al2O3 aluminium oxide. Aluminium is generally found in two forms, Al2O3, that is bauxite and corundum. So there are two forms also, alpha Al2O3 and gamma Al2O3. So alpha Al2O3 is also known as the corundum alpha Al2O3. There is a transition from gamma Al2O3 to alpha Al2O3. If gamma Al2O3 is heated to 1000 degrees centigrade then and heated simultaneously, then it changes to alpha Al2O3. So these are the few properties of Al2O3. Al2O3, as I have told you earlier, is amphoteric in nature, and this is all about the Al2O3. The next part would be the AlCl3.6H2O, that is aluminium chloride. Aluminium has a +3 charge, so it has a high heat of hydration, or I should say its hydration enthalpy is very more, so its water of crystallization is again high, so it has 6 water of crystallization, that is AlCl3.6H2O. So some of its properties or some of its reaction we will study now here. Aluminium AlCl3.6H2O. First would be the action of heat on the AlCl3.6H2O. When AlCl3 is heated, it forms Al2O3, that is corresponding oxide. I will not write the full reaction, I will just write the main compounds. That is, first would be the action of heat. So what happens that AlCl3, when it is heated, then it converts into Al2O3. So this aluminium oxide is formed, and evolution of HCl along with the evolution of HCl in the gaseous form. This represents that it is in the gaseous form and it is evaporized. Second would be the action of moisture on anhydrous AlCl3. So here would be the action of water H2O on anhydrous, mind you anhydrous, so it would be AlCl3. When it is reacted with water, it forms a white precipitate of AlOH whole thrice. A white precipitate of AlOH whole thrice is formed along with the evolution of hydrogen chloride gas. So this is the reaction, or this is the action of hydrolysis on the anhydrous AlCl3. The third would be the action of NH3. Now aluminium is bonded in AlCl3 is bonded with has 3 sigma bonds also. It has vacant 3p orbital. NH3 has lone pair, so it forms a NH3 donates its lone pair to the vacant orbital of aluminium through coordinate bond. So AlCl3, when it is reacted with NH3, it forms AlCl3 6 and AlCl3 6 NH3. By the way, its compound will be AlCl3.6 NH3. It is a solid compound. This is the reaction action of NH3. Now action of NaOH solution, and this is important reaction as far as this is concerned, because when NaH solution is added to a you say dropwise to an aqueous AlCl3 solution, then firstly a white PPT is formed. White PPT is formed of AlOH whole thrice. AlOH whole thrice, white precipitate is formed. But however, when we continuously again try to add NaOH more and more, so it dissolves. Excess NaOH, it dissolves because of the formation of sodium aluminate, that is NaAlO2. It dissolves in the excess NaOH, and this is used in the as a distinction of this cation from MgCaSr and barium, that is magnesium, calcium, and so it is used in the inorganic salt analysis. This is a very important reaction. Gelatinous white PPT. So if we are adding first dropwise adding NaOH to the aqueous solution of AlCl3, white gelatinous PPT is formed. But if we again continuously adding NaOH more, then it dissolves due to the formation of NaAlO2. And if this reaction is happening, if we are examining this reaction, then it can be confirmed that it has aluminium cation in its salt, and it is used as the test to distinguish from MgCa barium and strontium. Very important reaction as far as inorganic salt analysis is concerned, used as a reaction for the aluminium test for the presence of aluminium cation in the salt. However, if we have to separate the aluminium and zinc cation, both get dissolved in the excess of NaOH, so you cannot separate aluminium and zinc cation by this. For this, there is action of NH4OH solution. So for this case, if you add NH4OH solution to AlCl3, again white gelatinous PPT of AlOH whole thrice is formed. However, now addition of NH4OH more NH4OH will not dissolve this white gelatinous PPT. However, if it is zinc in place of the ZnCl2, then it gets dissolved. So this is used as a distinguish test between the aluminium and zinc cation. Very important reaction again, so I should mark it as an important. Yeah. Next will be the hydrolysis of water. AlCl3 has vacant orbitals. It attacks and undergoes hydrolysis to form produce AlOH whole thrice, which is a weak base, and also produce HCl. So HCl is, you know, that very strong acid. So AlCl3, you can say, is basically on hydrolysis is an acidic in character. Hydrolysis is acidic in character. So this was all about the AlCl3 or aluminium chloride. So next would be the alums. So alums are very popular. It has a general formula of M2 SO4 M-2 SO4 whole thrice dot 24 H2O. Here M ion would be generally alkali metal ion or a monovalent ion. However, Li plus is not except Li plus I should say, because Li plus, because of its very small size, cannot fit in the lattice or cannot form the corresponding crystal lattice. M dash ion, this is for the M dash here is used is generally a trivalent cation, that is Al plus 3 or Ga plus 3, In plus 3 or Tl plus 3. So this is the formula or general formula for alum. One would be potash alum, quite used for the purification of water, K2SO4, Al2SO4 whole thrice dot 24H2. This is also known as potash alum. So this was one. So this is all about, I should say, aluminium and its all compounds. Gallium, indium and thallium are not, there are not many compounds to study or are not of more relevance as far as all the competitive exams and NCERT is concerned. Most important are boron and aluminium. So I have covered most important compounds of boron and aluminium. So this is all about the group 13. Now moving on to group 14, that is carbon family. Let's talk about group 14 elements, that is carbon family. Second group 14, that is NS2, NP2 would be the general electronic configuration. So here I should write group 14, which would be Con, C, Geeta, Sneha and so it would be carbon, silicon, germanium, tin and lead. So it constitutes the group 14 elements. Electronic configuration, as I told you earlier, would be NS2, NP2. Group number, as it suggests, it would be 10 plus number of valence electrons, which are 4. So it would be group number 14. Talking about its general properties, first would be again the atomic radii. As we go down the group, the atomic radius should increase, and that is the correct order. However, there is slight changes in between the tin and Pb. However, it is not that important. Generally, as we go down the group, the atomic radii increases. The next would be the ionization energy. Ionization energy, as we go down the group, decreases because atomic radii increases, so ionization energy would decrease. Electronegativiity, however, all the electronegativities of all the elements are not that much, but carbon is the most electronegative element among the group 14 elements, and carbon also shows negative oxidation state in some of the compounds. Let's say in carbides, in methanides and alkylides, it shows a negative oxidation state. I will talk about more carbides in the later part of this lecture. So it also shows the negative oxidation state. Carbon also shows the negative oxidation state. Physical properties, as so to say, carbon and silicon are you can say non-metals. Germanium is a metal, a metalloid, and tin and lead are metals. So it is, this constitutes non-metals. This is metal and metalloid, and these are metal. This is the division of the group 14 elements. Now moving on to their reactivity towards oxygen. They react towards oxygen, but as we go down the group, the inert pair effect come into account. They show 2 oxidation state, plus 2 and plus 4 oxidation state. So as we go down the group, the stability of oxidation state of plus 4 decreases, and the stability of oxidation of plus 2 increases, because of when we eliminate these 2 electrons from the p orbitals, the effective nuclear charge on this s orbital electrons is very high, and these s electrons do not participate in bonding. Therefore, as we go down the group, plus 2 oxidation stability of plus 2 oxidation state increases, and plus 4 oxidation state decreases. Therefore, Sn and Pb in their plus 4 oxidation state acts as quite a powerful oxidizing agent, because Pb plus 4, Pb just plus 4 tends to go into Pb plus 2 quite readily. Therefore, it is very oxidizing agent. The Pb plus 4 acts as a very strong oxidizing agent. Not Sn plus 4 is not as oxidizing agent as Pb plus 4, but again in some circumstances and some conditions, Sn plus 4 can also act as a powerful oxidizing agent. So this was about the stability of plus 2 and plus 4 oxidation state. Now as far as the reactivity towards oxygen is concerned, then CO2, SiO2 and GeO2, that is oxides of carbon, silicon and germanium, are acidic in nature, and of SN and PB are amphoteric in nature, that is SnO2 and PbO2 are amphoteric in nature. SnO and PbO are also amphoteric. PbO2 is a very strong oxidizing agent because Pb exists in +4 oxidation state. Now next would be the reactivity towards halogen. These group 14 elements form two types of halogen, that is MX2 and MX4. Now MX2 is not very predominant as far as the carbon is concerned, but the MX2 and MX4 are formed by all the other compounds. Pb, but again is more stable in MX2 form, and Sn is also more stable in MX2 form. PbF4 is also found in nature. PbCl2 is also, Cl4 is also found in nature. However, PbI4 doesn't exist, is very unstable or doesn't exist because the PbI, the formation of the bond of PbI, because of this the energy should release is not very much to compensate the knockout the electron of 6s electron to unpair the electron. So the energy released by PbI, bond formation of PbI, is not enough to unpair the electron of 6s and move it to excite it to the next higher orbital so that it can form 4 bonds. Therefore PbI4 doesn't exist in nature. So PbI4 doesn't exist in nature. This is an important thing to note. So this was the reactivity towards halogen. Now again carbon also has anomalous properties which are different from rest of the elements. So carbon, because of its small size and relatively high electronegativity, has many properties which are different from the other elements. Carbon can form bonds with itself or some high electronegative elements. Let's say it can form C double bond C, it can form with oxygen also, it can form with sulfur also, and it can form with nitrogen also, triple bond also. So it has this property that it can form these bonds and of the small electron, because of the higher electronegativity of the combining atom and the small size of the carbon atom. This is not shown as we go down the group because the orbitals of silicon or germanium are very large and the effective overlapping is very less in the case of the rest of the group 14 elements. So again carbon has no vacant d orbitals, therefore its maximum covalence can be 4. However, as far as silicon, germanium are concerned, their maximum covalence can exceed 4 because of the presence of vacant d orbital in these elements. Next with the catenation. Catenation is a very important property which is you can say an unique property of the group 14 elements, that it forms bonds with itself because of the high you can say their metallic bonding is very high as compared to the other group elements. So catenation property, if you say, then catenation property of carbon, because of its smaller size, is very greater than the silicon, which is greater than the germanium, and germanium is equal to the tin. However, carbon has a very large catenation property, and because of this catenation property it shows allotropy, and there are 3 allotropes of carbon, namely diamond, graphite and fullerenes. So we will talk about each one of them now separately. So first I will talk about the diamond. Diamond, most of you know that diamond has a very hard structure. Diamond is a very hard molecule, and or the most hard molecule or most hard structure which is found on earth is diamond. So diamond, each carbon has the sp3 hybridization in diamond. Each carbon is attached to other 4 carbons and has sp3 hybridization. The cc bond length in this case is 154 picometer. So diamond has all the sp3 hybridized carbon, bond length is 154 picometer, and it is all the 3D structure, and diamond is known to be the hardest substance present on the earth. The second of the allotropes of carbon is graphite. So graphite is a 2D, it is a compact of layers, that is there is one layer, there is van der Waals forces in between, through which it is a van der Waals force of attraction between the 2 layers, and one sheet is completely the van der Waals, because of the van der Waals forces, the distance between 2 layers is 340 picometer between the 2 layers, and between each layer the bond length is 141 picometer, that is which is less than the bond length in case of diamond, because in the case of graphite all the carbon are sp2 hybridized because there are 3 sigma bonds and 1 pi bond, and electrons are mobilized over the whole sheet of the one graphite. So it is mobilized over the whole sheet, so it is a very good conductor of electricity. Graphite is a very good conductor of electricity. In this case, all the carbon in the same sheet are sp2 hybridized. The third and the last one is fullerene, which is fullerene is obtained from graphite only. So when graphite is heated in the presence of electric arc, in presence of inert gases, that is an inert atmosphere, then fullerene is produced. The C60 fullerene, which is very recently discovered, is known as the Buckminster fullerene, which is a shape of a soccer ball. Buckminster fullerene, which is a shape of a soccer ball. So there are 3 allotropes of carbon. One is diamond, other is graphite, and third is fullerene. Out of these 3, graphite is the most stable allotrope of carbon as far as thermodynamics is concerned. So if we are talking about thermodynamically, graphite is the most stable allotrope of carbon. Now reaction of halogens or reaction of fluorine towards I should say in the allotropes of carbon, if you want to consider, then halogens do not react with diamond, that the diamond is inert to halogens. However, graphite reacts with fluorine at 500 degrees centigrade and form intercatenation compounds. Again, diamond is unaffected by concentrated acid, but graphites again react with concentrated acid and form meltic acid. So meltic acid, the formula of meltic acid would be the benzene ring and 6 COH groups on each terminal or each carbon. There are 6 COH groups. So this is also known as meltic acid. So carbon reacts with concentrated nitric acid and forms meltic acid, hot and concentrated nitric acid, meltic acid. So graphite reacts with, in fact not carbon, graphite reacts. However, diamond is very inert to these reactions. Now next would be silicon, gallium and silicon, germanium and tin. Both have the diamond like structure. Germanium has a property that it expands, the liquid germanium is a liquid, so it expands when it is turned into solid state. So it is a very peculiar property or unique property of germanium, bismuth and gallium. So it is very unique property that the liquid expands when it is turned to solid state. So now talking about the reactivity towards acids and bases. So because of carbon and silicon, the compounds carbon and silicon are not you can say dissolved in acids. However, the compound of tin are get dissolved in acid in dilute HNO3. SN dissolves in HNO3, dilute HNO3 and form stannous nitrate. As far as the uses of carbon is concerned, carbon can be used in many ways. Now talking about the compounds of carbon, the first compound that we are talking about would be carbon monoxide. So carbon monoxide, the first preparation of carbon monoxide, if you will try to react the red heat coke with the carbon dioxide, it will give you 2 moles of carbon monoxide. Carbon monoxide is prepared in this way. In the laboratory, the carbon monoxide is prepared by the dehydration of methanoic acid in presence of H2SO4. So it is a methanoic acid HCOOH. So if it is present with H2SO4 and heated, then it forms, then H2O is evolved from it and CO2 and CO and H2, sorry, CO plus H2O is formed. So this is, you can say, dehydration of methanoic acid. The same is oxalic acid. The same reaction takes place with oxalic acid also, that if oxalic acid in the presence of H2SO4, that is concentrated H2SO4 in case, and heated, then the same H2O is evolved, H2O is removed and CO plus CO2, both gases are produced in this reaction. It is also is oxalic acid, H2C2O4, oxalic acid. So this one is also one. Now on commercial scale, if you want to produce carbon monoxide, then it is produced by passing steam over the coke, that is so a mixture of CO plus H2 is produced, which is also known as water gas, that is carbon, and this is steam, H2O in steam form, that is, you can say, in gaseous form is produced, then CO plus H2. The combination of both is known as water gas. However, in case of steam, in place of steam, if we replace it with air, that is, if carbon is in air, then O2 is present, N2 is present, then it forms CO plus N2, that is, N2 is just acting as a catalyst, you can say. So CO plus N2, and this is known as producer gas. So as far as the industry is concerned, water gas and producer gas are very important two ingredients. So these are to be kept in mind. These reactions are important, that this mixture is known as a water gas and this mixture is known as the producer gas. Carbon monoxide plus nitrogen gas is producer gas, and carbon monoxide plus hydrogen gas is water gas. Now talking about the properties of carbon monoxide. Carbon monoxide is a colorless gas. It is a you can say neutral oxide, that is, it is neither basic nor acidic, so it is a neutral oxide. However, carbon monoxide is toxic in nature because it forms a complex with hemoglobin, that is, hemoglobin O plus. If carbon monoxide is there, then it forms a complex with carbon monoxide. Hemoglobin forms a complex with carbon monoxide, that is carboxyhemoglobin, and releases oxygen. So hemoglobin is not able to transport oxygen throughout the molecules or throughout the body, therefore it led to eventually death. So carbon monoxide is, this is also known as carboxyhemoglobin, and carbon monoxide is toxic in nature. Now carbon monoxide, you can say that carbon monoxide here is in +2 oxidation state. We know that carbon has a maximum oxidation state of +4, so it can act as a powerful reducing agent, and it can reduce some metal oxides into their forms and used in their extraction. For example, if we consider ferric oxide, that is Fe2O3, and when it is reacted with CO, then it forms CO2 and reduces ferric oxide to iron, Fe. The same takes place in case of nickel also. So it can act as a powerful reducing agent. Now in coordination compound, you must have studied that carbon monoxide can also act as a ligand. Carbon monoxide also act as a ligand, so it is a powerful ligand property, and it is also used in the process for taking out the pure nickel. So NiCO4, when it is heated, or when it is Ni when is reacted with 4 molecules of carbon monoxide at 28 degrees centigrade, or I should say room temperature, it produces NiCO4, which then again heated, that is it is here CO act as a ligand, and when again it is heated to 180 degrees centigrade, it gives Ni plus 4CO. This nickel produced is very pure. And this process is known as Mond's process. Mond's process, and it is you will learn it further about in extractive metallurgy about the Mond's process. Very pure nickel is produced by this reaction. So it acts as a powerful reducing agent. It is a toxic in nature. Some of the properties, it is toxic in nature, it is neutral, and it is acts as a powerful reducing agent, and it can be used for extraction of some metals, and it is also used in Mond's process. Yeah. Some of the other reaction of carbon monoxide. Carbon monoxide is a very important compound, and it is used in quite a reaction. So carbon monoxide is, when reacted with chlorine, it forms carbonyl chloride, which is also known as the phosgene gas, which is very poisonous in nature. That is, carbon monoxide when reacted with Cl2 forms CoCl2, which is carbonyl chloride, but popularly it is known as phosgene, and it is very, very poisonous in nature. Carbon monoxide also reacts with sulfur and forms carbonyl sulfide, that is COS. So these are the two reactions. This is phosgene, very, very poisonous gas in nature. So this was all the properties of carbon monoxide and some of the important reaction of carbon monoxide. We will again you will encounter some of the other reaction also in the questions or in the advanced level. There are some, I am not talking about all the reactions because I am talking just about the important reaction, but there are some other reaction also which you can simply balance because they are very easy, but the most important reaction which have been asked previously in here and which are most likely to be asked in the coming years in all the competitive exams, and as far as NCERT and CBSE board is concerned, I am talking about all those reactions for this time being. So the next would be the carbon monoxide. Most of you will be familiar with the carbon monoxide, that is CO2. CO2 is a anhydrous, or you can say oxide of H2CO3, anhydrous oxide of H2CO3. So when 2 moles, 2 hydrogens are removed from H2CO3, then CO3 minus is formed, and this CO3 minus, when reacted with 2H plus, that is proton, it forms H2O plus, CO2 gas is evolved. CO2 gas is evolved. So the industrially, if you want to say how the CO2 is produced, then it is produced from quicklime, and in fermentation process also, that is a quicklime CaCO3, when it is heated to about 1000 degrees centigrade, it decomposes into CaO plus CO2 gases evolved. This is the industrial production, or this is the industrial preparation for carbon monoxide. And as far as fermentation is concerned, then you will know about this, the C6H12O6, that is also known as a glucose. When it is fermented, then it forms 6CO2 plus 6CO2 plus 12H2. Oh, sorry, I should say C2H5OH, that is ethyl alcohol, plus CO2. So it is 2 here would be, and it would be 2 here. I think this is balanced now. So this equation is balanced. Yeah. So glucose, this is known as fermentation process. Fermentation, by the action of bacteria, it decomposes into the ethyl alcohol, and carbon dioxide is releases subsequently. So again, you will be familiar with the photosynthesis reaction, that in photosynthesis, the 6 molecule of H2O and 6 molecule of CO2 and 12 mole of H2O reacts in presence of light and chlorophyll to produce the glucose and fructose, that is C6H12O6 plus 6O2 plus 6H2O plus 6H2O. So this is the photosynthesis reaction. By this process, the plants make their food. So CO2 is also used in the soft drinks. You must be known that CO2 at the high pressure has very good dissolving power, so it is used in the soft drinks also. The next would be carbon suboxide, that is C3O2. It is thought to be in a structure of C double bond C double bond C double bond O double bond O. It is also known as carbon suboxide. It is planar in structure, that is linear. So it is, you can say, I should rather say linear, because the central atom carbon has a hybridization of sp. This was about the carbon suboxide. Then it comes the carbonates and bicarbonates. You must be knowing about the carbonates. Carbonates is CO3 2 minus, and bicarbonates is HCO3 minus. So when two hydrogen are removed from the H2CO3, that is carbonic acid, then minus 2H plus, then CO3 2 minus is formed, and if only one proton is removed, then HCO3 minus is formed. So this was all about the carbonates and bicarbonates. The next we will be talking about carbides, very important topic as far as all the competitive exams and boards are concerned, carbides. So let's talk about carbides. Binary compounds of carbon with the other elements are known as the carbides. So there are 3 types of carbides: ionic carbides, covalent carbides, and interstitial or metallic carbides. So first I will talk about ionic carbides. Now ionic carbides are also there are 3 types of ionic carbides based on their product of hydrolysis. They are defined as methanides, that is, here all the carbides which on hydrolysis produce methane gas are categorized under methanide carbides. For example, Al4C3 on hydrolysis gives you can say CH4 plus 4 plus AlOH whole thrice. So you can balance the equation. It is a simple equation. So this is the reaction. So on hydrolysis it gives methane, therefore it is listed under the methanides carbides. The other example of it is Be2C, that is beryllium carbide. Second type of carbides in this category are you can say ethanides, acetylides or ethanides, acetylides. These give on hydrolysis the carbides give acetylide as one of the product. So for example CaC2 on hydrolysis gives acetylide, that is C2H2 and CaOH whole twice. This is the reaction. Another examples of this would be SrC2 or MgC2, both are of this the same form. Third would be allylides. So this gives 1 propine on hydrolysis. The you can say this gives 1 propine on hydrolysis. The carbides under this category gives 1 propine on hydrolysis. So for example, in this you can say Mg2C3 when hydrolyzed with H2O gives 1 propine, that would be CH3C triple bond CH plus MgOH whole twice. So in this case, in the case of methanide, carbon is in here the C minus 4 ion is present. So I have talked to you earlier that carbon can also show negative oxidation state, and I have stated earlier in the lecture that I will talk about carbides later. So here I am talking about that carbon here is in -4 oxidation state in this case. In this case carbon there is a C2 2 minus. In case of acetylides it is C2 2 minus. So it would be something like, I should say, C triple bond C and 1 lone pair, and this would be 2 minus. So this would be the anion of CaC2 in the acetylides. And as far as allylides is concerned, it is C3 4 minus, C3 4 minus, and its structure would be C triple bond C, and it would be here 4 minus 1 and 1. So here would be something like this. So in this case the anion is C3 4 minus, in this case it is C4 minus, and in this case it is C2 2 minus. So based on this anions and their hydrolysis product, the ionic carbides are further differentiated into 3: methanides, acetylides and allylides. And it is important because it is important topic as far as all the board exams and other competitive exams are concerned. So next would be covalent carbides. Covalent carbides, CO2, in which the element you are bonding with is non-metal, it would be covalent carbide. So it can be CO2 and CH4 or CH2, all are considered as covalent carbides. The next would be interstitial carbide. Now interstitial carbides are the carbides formed with the transition elements or D block elements, I should rather say D block elements. So D block elements have their metal lattice. There are holes in the metal lattice. There are octahedral holes and tetrahedral words. So tetrahedral words and octahedral words are present in the metal lattice of any metal compound. So as far as in the case of transition elements, the carbon can reside in the octahedral void, and this changes the property of the metal lattice, and this is called as interstitial carbide. They are very high boiling point and high melting point, and they are very tough. For example, WC, that is tungsten carbide, has a very high melting point, and there are carbides of chromium, magnesium, cobalt also, which can be hydrolyzed by water or dilute acid. So this was all about the carbides. The next I am going to talk about is another compound of carbon and silicon, which is the second hardest substance on earth after diamond, which is known as carborundum, SiC. It has a 3D structure in which each silicon atom is bonded to 4 carbon atom, and each carbon atom is bonded to 4 silicon atom. So it would be SiC, which is popularly known as carborundum. So its structure is silicon, carbon, 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 and this is again attached to carbon. So it is a whole 2D sheet structure, that here it is again Si, here it is Si, it is carbon, here it is Si, carbon. So it is extended in all directions, carbon, Si. So each silicon is attached to 4 carbons and each carbon attached to 4 silicon. It is a very hard structure, second hardest structure after diamond, known as carborundum. So this was all about the compounds of carbon. Next we move to silicon. So silicon, as you can see, is the second element of the group 14 element and is the second most abundant element found in the Earth's crust. As far as the preparation of it is concerned, so when silica is reacted with carbon, carbon acts as an reducing agent and it reduces SiO2 to Si and forms CO2, that is carbon monoxide. So this is the preparation reaction for silicon. Silicon, again, it is not attacked by acids. SiO2 doesn't react with acid, but it reacts with hydrofluoric acid. Except hydrofluoric acid, it doesn't react with any acid, because when it comes in contact with HF, it forms H2SiF6, that is hexafluorosilicic acid. It forms, this is known as hexafluorosilicic acid. It forms when it comes in contact with HF with the evolution of hydrogen gas. So this is the reaction. So it is not attacked by any acid, however it reacts with HF and forms hexafluorosilicic acid. So this is a very important reaction, I should say, because it reacts with only HF, SiO2, that is silica. Now talking about the compounds of silicon, first compound would be SiO2. So to say, so SiO2 is a oxide of silicon, as a name, silicon oxide, and SiO has a very high bond enthalpy. SiO bond is very strong in this case, so it has a very high bond enthalpy. So it resists the attack by halogens, dihydrogen and most of the acids. However, it is attacked by HF and NaOH. So as I told you about the HF, now talking about the reaction with NaOH, the SiO2 reacts with NaOH and forms Na2SiO3, Na2SiO3 with H2 formation of H2. So this is the reaction with NaOH. It reacts with NaOH also. It reacts with HF also. So it is mostly, you can say, it is amphoteric in nature, SiO2. Now binary compounds of silicon, that talking about the silicate. This was about the SiO2. Very important topic is silicates. So binary compounds of silicon with oxygen are known as the silicates, and there are many types of silicates which I am going to talk about now. That SiO4 is the basic unit. SiO4 minus is the basic unit. Its structure would be Si here, O minus on each oxygen. So 4 bond pair, no lone pair, sp3 hybridized, tetrahedral in shape. So this is a tetrahedral unit, which is the basic unit involved in each silicate. So depending on the number of oxygen that have been shared by a polymer, the different silicates are produced. So now I will talk about each of the silicate in detail. The first to be discussed is the orthosilicate, or which orthosilicate. So this contains, I should write orthosilicate. So this contains SiO4 minus as the basic unit. So simply SiO here and 4 minus. This is the basic structure of orthosilicate. This is considered the orthosilicate. So for example, it is found in zircon, that is Zr, zirconium, SiO4. So here zirconium in its +4 oxidation state and SiO4 4 minus, so it is an example of orthosilicate. The second will be pyrosilicates. In case of pyrosilicates, one of the oxygen is shared. So the basic entity would be, in this case, Si2O7 6 minus. So now I am representing silicon. I am going to draw the structure. So representing silicon by a dot and oxygen by O. So the structure of Si2O7 will be something like that Si is here, oxygen, and this oxygen is shared. So this is shared by here, and it has O minus, and here it is another oxygen, here another oxygen, O minus, O minus. So you can say this is the basic entity, or so to say, yeah, this one is basic entity, this one is basic entity, and this oxygen also has negative charge, and this oxygen also has negative. That is, there is this oxygen I am showing on plane of the board. It is oxygen coming out of the board. So all the oxygen have negative charge except the oxygen which is shared by to the both units. That is, it is connected to both silicon atoms. So the rest of the charge has negative charge. So it is 7 oxygen atoms and 2 silicon atoms. So it forms Si2O7 6 minus would be the basic unit of it. The example for this would be Sc2Si2O7. Sc2Si2O7 is example for pyrosilicates, for this type of silicates. So minus charge will be present only which is bonded with only one silicon atom. So this was pyrosilicate. Next would be cyclic silicates. So these were two orthosilicate and pyrosilicate. The next I am talking about the cyclic silicate. So in this case of pyrosilicate, only on orthosilicate no oxygen was shared. In pyrosilicate 1 oxygen was shared. In case of cyclic silicate 2 oxygen atoms are shared. In case of cyclic silicate 2 oxygen atoms are shared, and the common formula, or for the general formula, would in this case would be SiO3 N on 2N minus. This is the general formula for this type of cyclic silicates. So for example, if I am going to talk about Si3O9, that is Si3O9 would be 6 minus. So the structure for it would be that here is a silicon atom, oxygen here, oxygen here, oxygen here, and one oxygen coming out of the plane. This oxygen is again shared by another silicon atom here, one, here oxygen again, here oxygen again, and this oxygen is again shared. So here it comes and a silicon atom, and this oxygen is shared, and this is here. So it would be something like this. This would be structure of the, you can say, Si3O9, that this is one entity, this is second entity, and this is third entity. So these are the 3 entities of Si3O9. So, and the negative charges would be on here minus, minus here, minus here, 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 and here it is minus. So it is Si3O9 6 minus. So it is forming a cycle. So it is also known as cyclic silicate, and it should be SiO3 and 2 minus. So just keep in mind cyclic silicate, about the structure of cyclic silicate and the basic entity. So then another would be this third type of, another would be chain silicate. Now chain silicate again are of 2 types. One is the, we can say, single chain silicate, and other is the double chain silicate or cross-linked silicate. So we're talking about the chain silicate. So if first I am going to talk about the simple chain silicate. Simple chain silicate also has the same formula, that is, it also has the only 2 oxygen shared. So SiO3 2N minus is the same formula in this case also. However, in this case what happens is, if this is oxygen, this is sulfur, oxygen here, and here. So now this is one entity of this. Now here happens something like this, that here it is silicon again, and here it is oxygen, and here it is oxygen again. So, and the same happens in this case also, that here it is silicon, oxygen, oxygen, oxygen here. So it is continuous. So I have drawn 3 entities of SiO3 in this case also. So here is one, here is the second one, and here is the third one. So negative charge would be on this one, this one, this one, this one, 4, 5, and 6. So there, I have drawn correctly, 1, 2. This will also have the negative charge in this case also. So this is how we draw, but it do not have the negative charge, because this again are connected to some other. So in this case, this is a single chain silicate, it will expand in both direction. So this is a simple chain silicate having the same molecular formula SiO3 and 2N minus. Now in case of double chain silicate, or I should say three molecules or three oxygens are shared, therefore it would be something like two simple chain joined by connected by another oxygen atom. So it will, there are three number of oxygens shared. In case of double chain silicate would be 3. So its structure would be something like this, that here it is oxygen, silicon, then oxygen, here it is oxygen, here it is oxygen. This is 1 unit of silica. So and this is again this oxygen and this oxygen. So this is a, you can say, simple chain in this case. However, you can extend it in the same direction, that is, it is oxygen here, sorry, here, here and here. Now this, both this, so this is one chain, this is second chain, this is second element, and this is third unit. Now this and this are again connected by some other, so it would be form an hexagon, that it is something like this, here, 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 and same for here also. So it would be oxygen here. So there is 5 unit, and this oxygen now I will combine and here. So this is compound. So this is again continued in both direction here. So this is double chain silicate. So it is a one single chain silicate, it is again another single chain silicate, but these are combined by this common oxygen. So in this case 1, 2 and 3 oxygens are shared, this one and this one, 3 oxygens are shared. Therefore its general molecular formula of this would be Si4 O11 N6N minus. So this is the general formula, or this is a basic entity for this case of silicate. So it is a hexamer, you can say, 6 units of 6 basic units, SiO4 units, which combine to form the 1 unit of double chain silicate. The next would be 2-dimensional thin silicate. So in this case 3 oxygen atoms are again shared, and in that case the general formula would be Si2O5 2 minus. So it is a 2-dimensional chain silicate, and in case of 3-dimensional, all the four oxygen atoms are shared, so it is simply SiO2. SiO4, which is known as quartz, also used in quartz and some other chain also. So it is for the 2-dimensional, for the 3-dimensional, all the 4 are shared, and in case of a single chain and double chain, 2 and 3 are respectively shared. So many questions have been asked on silicates in the previous years, and it is a very important topic, silicates, so as far as the P block is concerned. Next would be silicons. This was about the silicates, now talking about the silicons. So silicons are of the form of, you can say, R2SiO units, synthetic organosilicon compounds of R2SiO units, which are held by SiO-Si linkage. So these are held by SiO-Si linkage. R2SiO2 is there, you can say, general formula. So how these are prepared? So when RCl is reacted with silicon in presence of copper and light, so it forms all possible, that is R3SiCl plus R2SiCl2 plus RSiCl3. It forms all these 3. Now depending on this, you can form, depending on this, in the hydrolysis of this will form the silicons of this form. That is, if you hydrolyze this, then it will form R3SiOH and 2 units of R3SiOH, that is, it will be SiOH R plus OH Si R. So when remove one molecule of water from it, that is minus H2O, when both are reacted, then this is taken out and the thing which remains is Si R linked by the O, so SiO linkage, and here R and R. So this is R is an alkyl group. It can be any group, or here I am talking about the alkyl group. So here HOH. So this molecule is removed, and corresponding to this is formed SiO linkage, and this is known as the silicons. So silicons are formed in this manner. So different characteristics of silicon can be there. That if it is formed from, let's say, this one R2SiCl2, then there are two hydrogen atoms. So in place of there, it would be OH again here and OH again here. So it would be something like O here, O here, and it is extending in both direction. So it would be something like this, that it is extending in both directions. So it would be infinite in this case. In case it is limited, but in that case it would be infinite. So different amount of structure. In case of 3, it would be on the upper side also. So this is linear, this would be planar, and this is just for the R3SiOH, it was again a dimer compound. So based on the different combinations, different silicons are produced, and this is all about the silicons. So this was about the group 14. As far as the SN and PB are concerned, the most important effect of their inert pair effect, that as we go down the group, the lower oxidation state become more stable. So PB is more stable in its +2 oxidation state, PbI4 doesn't exist, Pb +4 or PbO2, Pb in its +4 oxidation state is a very oxidizing agent or very strong oxidizing agent. These were some of the properties of the SN and PB. Now this was all about the group 14 or carbon family. Now moving on to group 15, or you can say nitrogen family. Nitrogen family is consists of nitrogen, phosphorus, arsenic. So it would be Nana, Papa, Ashu, Sab Bimar. So it would be Nana, Papa, Ashu, Sab Bimar. So it would be nitrogen, phosphorus, arsenic, antimony and bismuth. So I just remind this by that formula that I talked about you in periodic properties. Even I don't remember that directly their name. So it is group 15 and very important group, because nitrogen and phosphorus in this have very important properties, and many of the questions have been asked in the previous years on these two nitrogen and from the nitrogen family. Yeah. So starting now, nitrogen family. Nitrogen family, as you know, has the electronic configuration of group 15 would be NS2, NS2, NP3. So number of valence electrons 5. So group number would be 10 plus 5 as it suggests. So it would be 15. 10 plus 5 would be 15. So 5 valence electrons, group number 15. So talking about first their general properties. First would be electronic configuration, which is NS2, NP3. Second would be atomic radii. So as we go down the group, atomic radii increases in size. However, from arsenic to bismuth, there is a small decrease, small increase in covalent radius is observed from As to Bi because of that poor shielding of F electrons. Next would be ionization enthalpy. Ionization enthalpy, as we go down the group, decreases because of the increase in atomic radii. Next would be electronegativity. Nitrogen is the most electronegative element with an electronegativity of 3, and rest are less electronegative. So as we go down the group, electronegativity decreases. Talking about the physical properties, so all the elements of the group are polyatomic. Talking about the nitrogen, it is N2. For phosphorus, it is P4. It exists in P4 oxidation state, and the same is for arsenic, bismuth and antimony also. So all the elements of the group 15 family are polyatomic. Dinitrogen, as you know, is a gas, and rest of the others are solids. So dinitrogen is the only gas. So as far as metallic character is concerned, so metallic character increases down the group because non-metallic character decreases. So metallic character increases down the group. Now talking about the +5 oxidation state and +3 oxidation state. So group 15 shows +3 and +5 oxidation state. The same inert pair effect is shown in this case also. As we go down the group, +5 oxidation state becomes less stable and +3 oxidation state becomes more stable because of the non-participation of the S electrons in bonding due to the increased effective nuclear charge. So nitrogen, phosphorus, arsenic. So for bismuth and you can say antimony plus the oxidation state is more stable than plus 5 oxidation state. Again, nitrogen has the maximum covalence of you can say 4 only, because it has no vacant d orbitals, so only 4 atoms can be attached to it, to the nitrogen. Again, talking about the reactivity towards hydrogen, so if you're talking about the basicity, then NH3 is greater than PS3 is greater than ASH3 is greater than SbS3 is greater than BiS3. This is the stability basicity order, you can say, that is NH3 is more basic and BiS3 or you can say bismuth hydride is the least basic. Now talking about the reactivity towards halogen, so it forms you can say EX5 and EX3 types of halogens, where E is a group 15 element, EX3 and EX5 are the two types of which are formed by the nitrogen family. So talking about the hydrolysis is done. So in some case there is complete hydrolysis, in some case there is partial hydrolysis. For example, in case of SbCl3, it reacts with, on doing hydrolysis, it reacts with SbOCl, which is a precipitate, which is in orange in color, orange, and 2HCl. The same happens with BiCl3 also, that BiCl3 plus H2O is gives BiOCl, which is white in color, and 2HCl. So this reaction is also used in the quantitative analysis of the Sb plus 3 ion and bismutyl ion, that is Bi plus 3 ion. This equation is used, the hydrolysis is used as their reaction in quantitative analysis. So SbOCl, it is a partial hydrolysis, only one H2O molecule is added and the precipitate is obtained. Yeah, so this was the reactivity towards halogen. Now talking about the individual, that is coming on to nitrogen. Nitrogen, as you know, in the air has around 78% of portion is nitrogen or dinitrogen. N2 is a very inert gas. N2 is a very inert gas, and at room temperature it is very unreactive. So as far as the preparation is concerned, it is prepared by heating a mixture of NH4Cl and NaNO2. So when this is heated, ion exchange reaction takes place and NH4NO2 and NaCl is formed. Now in this NH4NO2, it is further heated. On heating it further, it produces the N2 gas and 2 moles of H2O. So it is a very important reaction, important for the preparation also, and this heating reaction is again very important. The NH4NO2 gives N2 on heating. It is a laboratory method of preparation for N2 gas. The same another is by heating ammonium dichromate, that is NH4 whole twice Cr2O7. On heating ammonium dichromate, we get N2, so it is a redox reaction, N2 plus H2O plus Cr2O3. So Cr is now in plus 3 oxidation state, so it is reduced from plus 6 to plus 3 oxidation state, and nitrogen has oxidized from minus 3 to 0 oxidation state. You can balance the equation, it is a simple redox reaction. So this is also again an important reaction. Several times it has been asked in the competitive exams that what happens when ammonium dichromate is heated, which gas is released. So the answer would be simply nitrogen in that case. So it is nitrogen gas here. Now talking about the oxidation of ammonia, it can also be prepared by oxidation of ammonia. So there is also two different types. One is at lower temperature. So if we are talking about the mixture at lower temperature, so ammonia, when ammonia is mixed with chlorine gas, that is ammonia is mixed with chlorine gas in the ratio of 8:3, then it is formed that NH4Cl is formed and N2 gas is evolved. So and this, but it would be 6, yeah. So this is at the lower temperature, that 8NH3 reacts with 3 moles of HCl2 forms N2 gas. This is at the lower temperature. If excess of Cl2, here the Cl2 is a limiting reagent, you can say, if excess of Cl2 is used, Cl2 is used in excess, then NCl3 is formed, nitrogen trichloride, and N2 gas is again NCl3 and 3HCl is formed. NCl3 is a very explosive element, very explosive compound, I should say. That is nitrogen trichloride is very explosive. If excess of chlorine is used, then NCl3 would be formed. So this is the reaction for this. So it would be 2 here, I think, or 3. Yeah, 3 NH3 plus 3Cl2 gives NCl3 plus 3HCl. This was the reaction at lower temperature. Now talking about at the higher temperature, what happens when the temperature of the system or temperature of the environment temperature is high, then what reaction takes place? So temperature is high, then NH3 plus CuO, that is copper oxide, cuprous oxide you can say, because cupric oxide, copper is in +2 oxidation state, so it will be cupric oxide gives you N2 plus 3Cu. So it would be reaction, and you can balance the hydrogen and oxygen by addition of H2O. So this would be the reaction in at higher temperature. This takes place. This is again the preparation of nitrogen. We are talking about the preparation of nitrogen. However, if you want to produce very pure nitrogen, that barium azide, that is BaN3 whole twice, azide is N3 minus, N3 minus ion is known as azide ion. So BaN3 whole twice, when it is heated, then very pure nitrogen, that is barium plus 3N2 is produced, and this is very pure nitrogen is produced by this sodium azide on heating. Same is barium azide, same happens with sodium azide also. The same reaction takes place in place of barium, that is sodium, and 3/2 moles of nitrogen. So the same reaction takes place in this case also. These were all the methods of preparation. Now talking about the properties, N2 is, as I told you earlier, very inert gas, colorless, odorless. It is not combustible, not a supporter of combustion, and it reacts with the magnesium, calcium, aluminium, and beryllium, as we have talked earlier in the S block elements about that lithium, beryllium, and magnesium, or alkaline earth metals, and lithium are some of the metals in the S block elements that react with nitrogen directly. So for example, the lithium reacts with nitrogen to form Li3N, that is lithium nitride. So this was the example, and Mg also react with nitrogen to form Mg3N2, which on hydrolysis gives MgOH whole thrice, which is a precipitate or white precipitate. So sorry, this is not a precipitate. MgOH whole thrice, it is corresponding hydroxide. Yeah. Again, another property would be that it has been used in Haber's process. You must be familiar with Haber process, that at 200 atmosphere and 500 degrees centigrade, in the presence of iron catalyst or molybdenum catalyst, molybdenum promoter, N2 combines with H2 to form ammonia. So it is one of the important properties of N2 and used as the preparation of ammonia, that N2 combines with 3 moles of H2 at the temperature 200 atmosphere and 500 degrees centigrade in the presence of iron, Fe as a catalyst, and molybdenum as a promoter. It forms 2 moles of NH3. So this was all the reactions of nitrogen. Now talking about the compounds of nitrogen, first would be definitely ammonia. I have talked about the preparation. This is the Haber's process by which ammonia is prepared. Another one more preparation would be from organic amides, that is CH3CONH2. When this organic amide is heated with NaOH, when it is heated with NaOH, then salt is produced, it is CH3COONA is produced, and corresponding to it NH3 gas is evolved. This is one of the preparation for the ammonia gas. This was all. So one more process which is an industrial process is cyanamide process. I should write it as cyanamide process. So in case of cyanamide process, CaO, that is calcium oxide, is reacted with coke and nitrogen gas 2C plus N2 at 2000 degrees centigrade gives CaCN2 plus carbon monoxide gas is evolved. This CaCN2 is when hydrolyzed, then NH3 gas is evolved. So this is a cyanamide process, an important reaction used as the industrial preparation of ammonia gas. Yeah. Now as far as physical properties is concerned, NH3 as you know has a lone pair, so it acts as a Lewis base. So in case of, you can say, in water, in the aqueous solution of NH3 reacts with the H2O, takes plus H plus, that is NH4 plus, and gives OH minus ion. So it is a Lewis base. NH3 is a Lewis base, and in aqueous solution of water of ammonia is a weakly basic, you can say, because of the evolution of OH minus ion. So it is weakly basic in nature. Now talking about the chemical properties. In chemical properties, it forms ammonium salts with acids. The NH3 forms ammonium salts with acids, for example NH4Cl, NH4 whole twice SO4, because NH3 reacts with HCl, NH3 reacts with HCl, that is hydrochloric acid, and forms NH4Cl, which is a salt. NH3 again reacts with H2SO4, and forms NH4 whole twice, so it will be twice here also, NH4 whole twice SO4. So these are the salts formed when reacted with acids. So NH3 reacts with acid and form the corresponding salts. Again, it acts, as I told you earlier, that it acts as a weak base in the aqueous solution. It precipitates the hydroxides of many metals from their salt solution. For example, when it is reacted with FeCl3, FeCl3 is when reacted with the aqueous solution of NH3, which is equivalent to NH4OH. So it precipitates out, that is, it forms FeOH whole thrice, or I should say not FeOH whole thrice, Fe2O3 dot XH2 plus NH4Cl. So this is a brown PPT of Fe2O3, ferric oxide brown PPT is formed. So it precipitates FeCl3 and forms brown PPT. So it acts as a you can say it precipitates out the aqueous solution of NH3, precipitate out the chlorides of or salts of metal ion or 3D, and the same happens with ZnSO4 also. ZnOH whole twice, which is a white precipitate, precipitates out when on the addition of NH4OH. But in case of NH4OH, as I have told you earlier, that NH4OH, if you excess of NH4OH is added to it, it dissolves the precipitate ZnOH whole twice, excess of NH4OH, excess dissolves and forms ZnOH whole 4 2 minus, yeah. So this is on excess of the addition of NH4OH, it dissolves and forms ZnOH whole 4 2 minus. In case if it is ANOH whole thrice, and if excess of OH whole thrice and excess of this NH4OH is added, then the same reaction will not take place, it will not dissolve. So this acts as a distinguish between the Al plus 3 cation and Zn plus 2 cation, and uses the inorganic salt analysis. It again NiCl2, it precipitates the NiCl2 CrCl3 CuCl2. So NH4OH acts as an precipitating reagent, so to say. Now the presence of lone pair of electrons on nitrogen atoms makes it a Lewis base, and it donates the pair of electrons and forms linkage with the metal ions and forms a very strong ligand. For example, Cu plus 2, that is cupric ion Cu plus 2, when reacts with NH3 ammonia. So ammonia has a lone pair, Cu has vacant orbitals. It forms, it is blue here, it forms Cu NH3 whole 4 2 plus coordination compound CuNH3 whole 4, which is deep blue in color. So this is the reaction in this case, CuNH3 whole 4 2 minus, so it forms a deep blue solution and it acts as a Lewis base and it acts as a Lewis acid. Here you can say it also acts as a ligand and forms a coordination compound. The same happens with in case of Ag, when the NH3 reacts with the Ag, you can say when the Ag reacts with the Cl, it forms AgCl, which is white in color and precipitates out. Now when NH3 added to AgCl, it replaces Cl from it and forms AgNH3 whole twice plus ion, which is dissolved in solution, or which is a colorless solution. So this was all about the properties of ammonia. Now talking about the test of ammonia gas or ammonium salt. The test would be the Nessler's reagent, very important reagent as far as the practical organic chemistry POC practical inorganic chemistry is concerned. In the practicals in the schools, you have might be done this Nessler's reagent test. So when NH3 gas is passed into the colorless solution of Nessler's reagent is K2HgI4 plus KOH is combinedly called as Nessler's reagent. So is colorless solution of Nessler's reagent, brown precipitate or coloration is formed. This is used as a test for NH3 gas. The reaction for this would be K2HgI4 plus KOH. This is combined called Nessler's reagent. When this is combined with NH3, it forms NH2 HgO HgI. So it is complex compound. This is a brown ring or brown in color is formed. This is the test for the NH3 gas and this is the Nessler's reagent. So this is the test for NH3 gas. So next would be the oxides of nitrogen, talking about the oxides of nitrogen. So the oxides, there are many oxides of nitrogen: N2O, NO, N2O3, N2O5, NO2. There are mainly 5 oxides of nitrogen, and some of them are acidic in nature, some of them are neutral in nature. We will talk about each one of them separately now. So we are talking about each of them separately now. So there are 5. There are N2O, NO, N2O3, NO2. Dimer of NO2 is again N2O4. This is an odd electron species, and NO2 is an odd electron species. NO is also an odd electron species. N2O4 and N2O5. Mainly these are the oxides of nitrogen that are important. So let's start with the N2O. N2O is obtained generally by heating NH4NO3. That is, when you heat NH4NO3 on heating, give N2O plus 2 mole of hydrogen, H2O, that is water. So it is a preparation step for N2O. And as far as the NO is concerned, so when you react HNO3, cotton concentrated HNO3 with copper, NO gas is produced. It is an odd electron species because the number of electrons in this would be 7 plus 8, that is 15. So it is an odd electron species. Now talking about the N2O3. N2O3 is a blue liquid or a pale blue solid, which can be just this is a mixture of NO plus NO2, that is NO plus NO2 when reacted together forms N2O3. So this is the preparation step for N2O3. Now talking about the next one, which is NO2. So NO2 can be a reduction of concentrated HNO3. So concentrated NO was prepared with Cu, that is Cu when reacted with HNO3 when HNO3 is dilute. Now the Cu when we react with HNO3 when it is concentrated, so the product will be NO2 in this case. However, in this case it would be NO. So this is the difference, that one here it is NO and other in this case it is NO3. So sorry, NO2. Now talking about the N2O5. N2O5 is an anhydride of HNO3, that is nitric acid, and it can be prepared by the reaction of P4O10 with HNO3, and which that is P4O10 when reacted with HNO3 gives us what is N2O5, gives us N2O5 plus HPO3 acid. So this is the reaction, and N2O5 is prepared by this step. Now talking about the properties, then first property would be that about the N2O, that N2O readily decomposes, or I should not, when heated, N2O when heated decomposes into nitrogen and oxygen into 2:1 ratio. So N2O is a good supporter of combustion, I should say, because it contains better supporter of combustion than air, because air has only 20% oxygen. However, the mixture of N2O will have 33% oxygen. That is, N2O when heated gives N2 plus O2. So it will be 2 moles here, 2 moles here, 1 mole, heating about 500 degrees centigrade. So it gives this. So this combination has 33% oxygen, and air has only about 20 or 21% oxygen. So this is a better supporter of combustion than air, this N2O. Now talking about the N2O3, it is an anhydride of HNO2. N2O3 is an anhydride of HNO2, and few reaction and reaction of N2O3 with KOH, that is a strong base, is that it neutralizes and forms KNO2 plus H2O. Talking about the nitrous oxide, that NO2 and N2O4 is a mixed anhydride of HNO2 and HNO3, that is N2O4 is anhydride of HNO2 and HNO3, anhydride, I should say anhydride of HNO2 and HNO3, then N2O4. So these are few of the reactions or few of the properties which you have to keep in mind. As far as the structure is concerned, now I should talk first about the structure of all this. First one was N2O, so it would be N, double bond N, double bond O here, it would be plus here or negative here. So it is 2 bond pair, no lone pair, sp hybridized, linear in shape. This is N2O. The next one was NO. NO is an odd electron species, so its hybridization should not be determined by the valence bond theory. So it is something like it has odd electron 1 and here, and it has 2 odd. So it is a different compound. You cannot predict its structure from the valence bond theory, because valence bond theory fails in the cases of odd electron species. So this is NO. Then it is N2O3. N2O3 is a very important structure. It has been asked in the JEE also, that N2O3, it is the structure that you will predict would be something like this, that N2O3 is this one, because it satisfies all the covalencies and all the bond length. But the structure of N2O3 is found out to be like something like this, that it has a bond here, here, and it donates to N2O3. So this is the structure for N2O3. This is wrong, this is correct. It is an NN bond. This is structure for N2O3. The next would be NO2. NO2 again is an odd electron species, so I am drawing the structure of its dimer N2O4, which is not an odd electron species. N2O4 has an NN bond. Here it is oxygen here, it is oxygen here, donating oxygen to here, donating oxygen to here. So it has sp 3 bonds, no lone pair, 3 bond pair, no lone pair, sp2 hybridized, planar in shape. This bond length is greater than the single NN bond length, because of the more repulsion of more closing the reaction, and the N2O4 is very unstable. I should not the lone pair. This compound is very unstable, N2O4 and NO2. NO2 is itself unstable, and N2O4 is again not very stable in this case. Now next would be the N2O5, and N2O5 is a NON bond, and here double bond O here, double bond O here, donates here. So 3 bond pair, no lone pair, sp2 hybridized, linear in shape. So this is the trigonal shape. This is the structure for all the oxides of nitrogen, and it is very important because previously the questions have been asked on the structure of the oxides of nitrogen. So this was all about the oxides. Now talking about the oxyacids of nitrogen. First would be nitrous acid, that is HNO2. It is an unstable weak acid, as it has only one proton available for protonation. HNO2 is a weak acid, and it is known only in the aqueous solution. when you are trying to concentrate, the acid decomposes, giving HNO3 as a byproduct. HNO3 and NO as a byproduct. So this was all about the nitrous acid. Coming out to nitric acid, that is HNO3. HNO3, very important compound. HNO3 and nitrogen in +5 oxidation state. It acts as a very powerful oxidizing agent. Besides, it is a very powerful acid, and it also acts as a very powerful oxidizing agent. Its concentrated form acts as a very powerful oxidizing agent. As far as the preparation of HNO3 is concerned, it is prepared by reaction of NaNO3 with H2SO4. So when H2SO4 is reacted with HNO3, so NaHSO4, that is sodium hydrogen sulfate, is formed along with HNO3 acid. So this is the preparation for nitric acid. As for on large scale, if you will say, then it is formed by the reaction of ammonia with oxygen, in presence of platinum or rhodium gauge at the temperature of 500 Kelvin and pressure of 9 bar. It forms the 4 molecules of NO plus H2O, and this NO combines with oxygen to form NO2, and this NO2, when hydrolysis of NO2 is done, it forms HNO3. So this is the complete reaction, and this is the whole process is known as Ostwald process. Industrially, the HNO3 is prepared by Ostwald process. Important reaction, keep in mind all this reaction that HNO3 is NH3 first react with oxygen in the presence of platinum or rhodium gauge at the temperature of 500 Kelvin and atmospheric pressure and a pressure of 9 bar, forms an nitrous oxide. When nitrous oxide is further ozonized, or I should say reacted with air, it forms the NO2, that is nitrous oxide, and this when reacts with the H2O, hydrolysis of NO2 is done, it forms HNO3, that is nitric acid. So this is the Ostwald process, and this is the preparation of HNO3. HNO3, as I talked about you earlier, that it is a very strong acid, and it has very strong oxidizing agent also and a strong acid also, and it attacks most of the metals except the noble metals, you can say, such as gold and platinum, and dissolves most of the metals in it. And the production, as far as the product of the oxidation is concerned, because it itself gets reduced, so it acts as an oxidizing agent. So product is depend on the concentration, on the temperature, and the other factors also. But the main factor of this would be the concentration of HNO3. If it is concentrated, highly concentrated, the oxidation state to which it is reduced would be less, and if it is dilute, the oxidation state to which it is reduced would be more, as in the case of which we saw in the case of copper, that when copper reacts with HNO3 dilute, it forms NO, where N is in +2 oxidation state. But when copper reacts with HNO3, where HNO3 is concentrated, it reduced to NO2, where N is in +4 oxidation state. So it depends on the concentration of nitric acid, what product will be formed on the other side. Yeah. So talking about some of the reactions of nitric acid, as you can say, its oxidizing agent, it oxidizes metals as well as non-metals. So I will talk about some of the reactions of HNO3 as its oxidizing agent for metals as well as non-metals. For example, if you are talking about the zinc, that is Zn, so there it is Zn. I will take 3 examples. One would be very dilute. When the concentration is very dilute, what would be the reaction? So in the case of very dilute, zinc reacts with HNO3. All these are the redox reaction because it is oxidation reduction reaction. Zinc reacts with HNO3, and most of the main important would be the compound formed. What would be the reduction of HNO3? So in case of very dilute, it would form about this would be same, that it will form ZnNO3 whole twice, but corresponding to it will form NH4 NO2. So in this case NH4 NO2 will be formed here. N is in -3 oxidation state, and in this NO2 minus, the N is in +3 oxidation state, so it reduces from +5 to -3 and +3 oxidation state. So the 8 difference oxidation state is 8 in some case, so very strong, very you can say reduces to very large extent. In the case of dilute, when dilute is used, then when zinc is reacted with HNO3 dilute, then the ZnNO3 is formed, and along with it N2O is formed. N2O, that is N here is in +1 oxidation state. In average oxidation state is +1. So it reduces from +5 to +1 oxidation state in case if you are using dilute nitric acid. And if we are using concentrated nitric acid, then the product would be the NO2, that is, it forms NO2. So this is the difference in the compound. So in the one case N is for NO2, when very dilute nitric acid is used, when dilute nitric acid is used, N2O is the product, and when concentrated nitric acid is used, NO2 is the product. This is the trend which is followed for all the other most of the other metals also. However, in some case there is slight deviation, but most of the time if concentrated HNO3 is used, NO2 will be the byproduct, dilute is used, N2O will be byproduct, and very dilute is used, then NH2O NO2 will be the byproduct. This was the reaction with metals. Now talking about the reaction with non-metals, HNO3 also acts as an oxidizing agent in case of non-metals also. So first I am talking about, let's say, iodine. What happens when iodine, it reacts with iodine? Iodine, HNO3. However, in case of here, we have to use only concentrated HNO3. Here it should not be dilute or something like that, it should be concentrated. So when you are using concentrated, it oxidizes I2 to HiO3, that is iodic acid, highest of HiO3, where iodine is in +5 oxidation state, HiO3, and reduces itself to NO2. The same in case of metals also. In metals also HNO3 was reduced to NO2. In here also it is reduced to NO2. If here it is carbon, then it will be CO2. If it is here phosphorus, it would be H3PO4, that is phosphoric acid, and if it is here sulfur, it would be H2SO4, that is sulfuric acid. So sulfur is in +6 oxidation state, phosphorus is in +5 oxidation state, and carbon in +4 oxidation state, that is corresponding oxidation, highest oxidation state of these non-metals. So you can see that HNO3 is a very strong oxidizing agent, because it is oxidizing the non-metals from 0 oxidation state to their highest possible oxidation state available. However, in case of I2, it oxidizes it to the +5 oxidation state only. However, +7 oxidation state for iodine is also available. Now for nitrate, there is a brown ring test which you will learn more about in salt analysis, in organic salt analysis, but I will just like to share some of the facts of the brown ring test. The familiar brown ring test for nitrates depends on the ability of Fe+2 ions to reduce nitrates to nitric oxides and gets itself oxidized to Fe+3, that is ferric oxide, and forms a brown colored complex. For example, NO3 minus, and here it is 3Fe+2 in acidic medium reacts and get reduced to NO, that is NO nitric oxide, plus Fe+3, oxidizes itself to Fe+3, and FeH2O whole 6 2 plus. This is the complex present in water. It reacts with the nitrogen formed, NO formed, and forms a complex FeH2O whole 5 NO. NO acts as a ligand, 2 plus, and H2O molecule is released. This is a brown ring test. So test is usually carried by adding dilute ferrous sulfate solution to the aqueous solution of nitric acid or containing nitrate ion, and then carefully adding concentrated H2SO4 along the side of the test tube. Along the side of the test tube, a brown ring is formed at the interface, and the brown ring is of FeH2O5 NO. So this is popularly known as brown ring test. Very popular test. This is brown ring test. Next, so this was all about nitrogen. Now talking about the phosphorus. Next we step up to phosphorus. So phosphorus occurs in nature in case of stable phosphates. It was a phosphorite and fluoride. There are many minerals in form in which phosphorus is obtained. Now phosphorus is again also shows allotropy, and there are most 3 allotropes of phosphorus: white phosphorus, red phosphorus, and black phosphorus. So I will talk about each of the allotrope one by one. So first it would be white or yellow phosphorus, that is it exists in the P4 molecule, it exists as a P4 molecule, something like this, that P, 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 P. This is I am drawing about the white phosphorus, So, and this again are linked to and cell. So this is sp3 hybridized, and it has an angle of 60 degrees, so it's very strained, so it is highly reactive. This is structure of white phosphorus, that white P, it is a structure of white phosphorus P4. It is very reactive because of the very high angle strain of 199, it is 60 degrees, so 49 degree angle strain, very high angle strain. So talking about white or yellow phosphorus, then it decomposes P4, if it is heated to greater than 800 degrees centigrade, it decomposes into, begin to dissociate into P2 molecules, white phosphorus. Now the conversion of white phosphorus to the red phosphorus, it is a very interesting conversion, that white phosphorus converts into red phosphorus if it is heated to about 250 degrees centigrade. It requires an inert atmosphere of N2 gas or CO2 gas, whatever, and iodine as a catalyst. So inert atmosphere of N2 or C2 and iodine as catalyst. At the temperature of 250 degrees centigrade, white phosphorus converts into red phosphorus. However, red phosphorus again convert into white phosphorus when it is heated to 550 degrees centigrade, and inert atmosphere again is required for this conversion, and then it is cooled at room temperature, then red P again converts into white phosphorus. So this is the conversion of white phosphorus to red phosphorus and red phosphorus back to the white phosphorus. Important reaction. So this is also used as the preparation of red phosphorus. Red phosphorus is something, you can say red phosphorus is a polymeric or a chain structure, that P, 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 P. This is participates in this here. So this is the red phosphorus, and this continues. So red phosphorus is a chain which takes place here. So it is again red phosphorus. So P4 again reacts with NaOH, as I told you earlier, that it reacts with NaOH and forms phosphine gas and sodium hypophosphite, that is NaH2PO2. So this is the reaction of P4 with NaOH or alkali metal. Now, so this was the white phosphorus, this was the red phosphorus. There is one more allotrope of phosphorus, which is black phosphorus. Black phosphorus is very stable. It has two forms, alpha black phosphorus and beta black phosphorus. So alpha black phosphorus is formed when red phosphorus is heated at the temperature in a sealed tube at 803 degree Kelvin. Now beta black phosphorus is a good conductor of electricity, whereas alpha black phosphorus is non-conductor. So phosphorus, I should say, the black phosphorus has the structure something like this here, and this again is shared. So hexaring or 6 molecules in the same thing, and this again is shared. This again here is shared. So this is the black phosphorus, and it is just a linear chain, and it is a 2D chain, or it is type of a sheet. So it is black phosphorus, and it is the most denser type of phosphorus. As far as the reactivity is concerned, white phosphorus is most reactive than red phosphorus and black phosphorus. The reactivity of white phosphorus is accounted because of the angle strain, and black phosphorus, this is about 120 degree, so it is very close to that of 109.5 degree. Therefore it is most stable, and its alpha form is beta form is good conductor of electricity, and alpha form is a non-conductor. So stability is white phosphorus most stable, then red phosphorus, and then black phosphorus. So this is what about the this thing. Now talking about the compounds, the first compound which we will be talking about will be the phosphine, PS3. There is one peculiar property about PS3, that hybridization doesn't apply to PS3. We doesn't apply hybridization to PS3, because if you will talk about, you will say PS3 is hybridization sp3, 3 bond pair, 1 lone pair, strike number 4, hybridization sp3, shape should be trigonal pyramidal. However, to the you can say shape is pyramidal. To PS3, hybridization is not applicable, and the lone pair resides in the s orbital. Lone pair resides in the spherical s orbital, and which makes PS3 less basic as compared to NH3, because we know that s orbital are most you can say spherical nature, so its tendency to donate its electron will be very less. However, NH3 will donate its electrons more easily, so PS3 is a weak base as compared to NH3, so NH3 is greater than PS3 as far as basicity, or I should say Lewis basicity is concerned. It is a Lewis basicity is concerned, PS3. So remind just one thing, that hybridization doesn't apply to phosphine or PS3 gas here. So we are talking about the PS3. So as far as its preparation is concerned, it is prepared from the hydrolysis of Ca3P2, that is calcium phosphide. When it is hydrolysis reacted with water, phosphine gas is produced and CaPH. It's one more reaction I told you just earlier, that when phosphorus is reacted with hot and concentrated NaOH, it forms it is disproportionate phosphorus disproportionate, and disproportionation reaction takes place, and PS3 and sodium hypophosphite, that is NaH2PO2, is formed. So these were the two of the you can say preparation step for phosphine gas. And phosphine gas acts as, when absorbed in copper sulfate or mercury chloride or silver nitrate, the corresponding phosphides are obtained. For example, if you want to talk about HgCl2, that is mercury chloride, reacts with the 2-phosphine and forms Hg3P2. This is brownish black in color. So these are some of the reaction. Phosphine, the most important characteristic about phosphine is that hybridization doesn't apply to phosphine, and it is a weak base as compared to NH3. Most of you will say that it should be the strong base, or what would be the reason for it to be weak? Because the lone pair resides in the s orbital and not the hybridized orbital, and the hybridized s orbital. Yeah. So this was about now talking about the oxy acids of phosphorus. So phosphorus has oxy acid H3PO3. So one of the property about H3PO3 is that it has the basicity 2 and not 3. Only 2 acids are there whose basicity is less as compared to the number of hydrogens. For example, H3PO3 is one of them, it has the basicity 2, and H3PO2 is the another one which has acidity 1. So its structure would be P double bond O, here it is OH, here it is OH, and here it is H. So one hydrogen is directly connected to phosphorus, and therefore it has basicity 2 only. This hydrogen and this hydrogen are available for protonation, so for the deprotonation, so it has basicity 2. And as far as the structure of H3PO2 is concerned, so it would be double bond O, OH here, and 2 hydrogen directly bonded to phosphorus atom, so it has basicity only 1. This is the only H which is available for deprotonation. So it has basicity 1 and it has basicity 2. These two are the only acids which have basicity less than the number of the hydrogens present in the acid. So this is an important compounds. Both are important compounds, and the structures of them are also important. Yeah. So talking about now phosphoric acid or orthophosphoric acid is also known as H3PO4. H3PO4, it is formed by the hydrolysis of PCl5. PCl5 is when hydrolyzed, H3PO4 is formed. And so now as far as the properties of H3PO4 is concerned, then reaction with silver nitrate, it reacts with silver nitrate and forms Ag3PO4, which is a yellow precipitate, and these are some different properties of you can say H3PO4. So these were some of the oxy acids. Most of the important reaction would be H3PO3 and H3PO2. Just keep in mind their structure and their basicity is less than the number of hydrogen. However, its basicity is 3. Its structure would be something like P double bond O here, OH here, OH here, and OH here. So it has all the 3 hydrogen available for deprotonation. It has basicity 3, it has basicity 3, it has basicity 2, and it has basicity 1. So this was all about the oxy acids of phosphorus. Now these were the compounds, important compounds of nitrogen and phosphorus. As far as the arsenic, bismuth, and antimony concerned, we doesn't talk about much of the compounds of these 3 elements, most of the compounds which are relevant are of nitrogen and phosphorus. So this was all about the group 15. Now moving on to the next group, that is group 16, oxygen family. So group 16 has an electronic configuration of NH2NP4. Group number would be 10 plus the number of valence electrons, which in this case are 6. So group number would be 16. So group 16, I write here group 16, it is O style say T-O, that is oxygen, sulfur, selenium, tellurium and polonium. So this is the so talking about the atomic and ionic radii, down the group atomic ionic radii increases, ionization enthalpy, all the rest of the properties are same. I think I don't have to discuss this property. We have learned about this property in periodic properties and chemical bonding quite a lot. Now talking about the again anomalous behavior oxygen, because the d orbitals are not present, absence of vacant d orbitals, its maximum you can say covalence would only be 2. However, the other can, because of presence of s orbital, d orbitals, vacant d orbitals, can have their covalence greater than greater than 2. As far as the reaction with hydrogen is concerned, so all the hydrides except water produces reducing property, that is they reduce H. Now H2O doesn't have reducing property because H2O is highly hydrogen bonded, so it is not possible for it to remove the hydrogen or the produce the hydrogen and show the reducing behavior. Therefore, because of the hydrogen bonding in H2O, its reducing behavior is very low. Now talking about the important you can say compounds of the group 16, first would be obviously dioxygen, that is O2, the gas on which we all live, that is O2 dioxygen. First we will talk about the dioxygen. So it can be prepared, as far as the preparation is concerned, it can be prepared by heating the oxide, that is SgO, or you can heat MnO2, which are not very stable oxides. On heating to a certain temperature, about 200 to 300 degree temperature, they decompose into the corresponding metal and releases oxygen gas. So these are the some of the properties. It has isotopes, you can say 16O, 17O and 18O. There are 3 isotopes for oxygen atom, 3 isotopes. So next we will talk about the oxides. Oxides are so many forms. There are acidic oxides, there are basic oxides, there are neutral oxides, there are suboxides, there are superoxides, and there are peroxides. So these are the some of the categories. Amphoteric oxides are also there, and mixed oxides. So there are many oxides in oxide. So as far as acidic oxides are concerned, non-metallic oxides is mostly acidic oxide. Let's say CO2 is an acidic oxide because on addition of water it gives H2CO3, which is carbonic acid, which is acidic in nature. So CO2, SO2, SO3, all these oxides are acidic oxides. As far as the basic oxides are concerned, so Na2O and all the oxides of the metals of the, you can say alkaline earth metals and alkali metals, are most of the oxides are basic in nature. Amphoteric oxides, if you want to talk about the amphoteric oxide, then it would be oxides of aluminium, you can say Al2O3, less than O2, PbO2, all these oxides are amphoteric in nature. Neutral oxide, there are only few neutral oxides. One of them is carbon monoxide, one of them is N2O, and one of them is NO. So CO, N2 and NO, these 3 are the most popularly known neutral oxides. Then other would be mixed oxide. This is a new category. So mixed oxide, that is Pb3O4, is an oxide which is a mixed oxide of PbO2 plus PbO. It is a mixed oxide. So 2 moles of PbO plus 1 moles of PbO2 forms Pb3O4. It is a mixed oxide. Same is for Fe3O4 also. Fe3O4 also the same happens. It is also a mixed oxide. Mn3O4 is also a mixed oxide. Talking about the peroxides, H2O2, peroxides has O2 2 minus as their ions. So H2O2 is a peroxide, K2O2 is a peroxide, and all these are known as peroxide. Talking about the superoxides, superoxides has O2 minus 1 as their anion. So KO2, that is potassium superoxide, or CSO2, cesium superoxide. These are the some of the superoxide. And the last and the final is suboxide, in which the number of oxygen are relatively less than the number of central atom. For example, C3O2, that is carbon suboxide. It is C3O2 is one of them, N2O is one of them, Pb2O is again. These are categorized under suboxide where number of oxygen is less than the number of central atom. So these are the suboxide. Now talking about the next important reaction, next important compound, that is ozone or O3. So ozone has the structure of ozone, so resonance. So ozone has a structure here, double bond O minus, you can say here it has a positive a plus, and it shows resonance here. So it has a bond order, both the resonating structure are equal stability, so its bond order is 3/2, that is 1.5, and bond length is in between the single bond length and double bond length. Ozone, so as far as its preparation is concerned, then first oxygen is some energy is produced, energy is applied, so it breaks it into 2 oxygen atom, and this then combines with oxygen. This when combines with oxygen forms ozone molecule. Ozone is a dark blue gas and which forms a blue liquid on cooling, and solidification forms violet black crystals, and it absorbs most of the ultraviolet light, therefore it has a thin layer over the atmosphere. So ozone is very important layer as far as our atmosphere is concerned. Ozone is a very strong oxidizing agent because ozone has nascent oxygen, reverse nascent oxygen, which acts as an oxidizing agent and also used as a bleaching. It also has bleaching power because of this nascent oxygen evolved. It has a bleaching power and it also acts as an oxidizing agent. So if this oxygen acts as a very strong oxidizing agent, so if it oxidizes H2S to sulfur, and if it is sulfur, it oxidizes to +6 oxidation state. So if sulfur is in -2 oxidation state, it oxidizes it to 0 oxidation state, and if the sulfur atom is in positive oxidation state or 0 oxidation state, it oxidizes it to +6 oxidation state, that is the highest oxidation state possible. Most of the time when you will react ozone with the when you will oxidize any element with the ozone, it will achieve the maximum oxidation state. If it is in some plus oxidation state or in 0 oxidation state, it will achieve its maximum oxidation state. However, if it is in negative oxidation state, in case of let's say H2S, then it oxidizes to sulfur. So these are some of the things that you have to keep in mind. It is again show bleaching action. Because of this, it is used as in ozonolysis as a reagent in organic chemistry also. As far as test for ozone is concerned, so a filter paper soaked in alcohol benzidine, that is this benzidine would be 2 benzene rings and NH2 here and NH2 here. So this is benzidine. So a filter paper soaked in benzidine, alcoholic benzidine, becomes brown when brought in contact with ozone. So this is act as a test for ozone. So this was the compound ozone. So to summarize, it is a very strong oxidizing agent. It also acts as a bleaching agent because of the nascent oxygen evolved. Its structure is something like this. It shows resonance and it has the bond length between the single and double O bond length, and it oxidizes the metals or non-metals from - to its 0 oxidation state, and if the atom is present in 0 or some plus oxidation state, it oxidizes it to its maximum oxidation state. Most of the times this trend is followed. So next important would be the hydrogen peroxide. Hydrogen peroxide, that is H2O2, has a book-like structure. You can say a book-like structure and hybridization of sp3. The OO bond length in H2O2 is greater than the OO single bond length because of the repulsion here. It is something like this, H2O2 and 2 lone pairs. On this 2 lone pair, 2 bond pair, sp3 hybridization. Okay, yeah. So talking about the H2O2, so H2O2 decomposes into water and O2 slightly on exposure to light. So it is, you can say, photolytic. So when light is exposed to H2O2, it decomposes into H2O and oxygen. Therefore, H2O2 is not kept in glass containers because traces of alkali metal ions can catalyze the explosive decomposition of H2O2. So H2O2 again is an oxidizing in nature, oxidizing and reducing both. It can show both the case. It can oxidize also and it can reduce also, because oxygen here is in -1 oxidation state. So if it acts as an oxidizing agent, it goes to O-2 oxidation state, and if it acts as a reducing agent, it goes to O0 oxidation state. So it can act both as the oxidizing agent as well as the reducing agent, and it shows both the properties. Yeah, so this was all about the H2O2. Now talking about or moving on to the next important, that is sulfur. Now sulfur again shows allotropic forms. One is rhombic sulfur or alpha sulfur, and another is monoclinic sulfur or beta sulfur. Both are soluble in CS2, that is carbon disulfide, but the difference, the specific gravity and the bond length are different. Both have the crown puckered like structure, or I should draw the structure in the rhombic sulfur, but the metal lattice is different. You can appreciate the difference of this as when you will learn about the solid state, that what is the difference between the rhombic sulfur and monoclinic sulfur. So just I will just draw the diagram of the pucker like structure, crown puckered like structure of sulfur. So there are 8 atoms here. So and here it is here sulfur and here sulfur. So it looks like a crown, and this angle is 107 degree and the bond length is 204 picometer. So it is S8 form, and it is again in rhombic sulfur, I should say rhombic sulfur or alpha sulfur. Yeah. So next talking about, this is the rhombic sulfur. Next talking about the compounds of sulfur. First would be H2S or hydrogen sulfide. Hydrogen sulfide, as I have talked about their basicity, that hydrogen sulfide is more acidic than H2O. The reason for this being that H2S, whenever you have to comment on the acidity of any acid, just pretend what happen if we lose one H plus. It will be H plus and SH minus ion, and in case of H2O it would be H plus and OH minus ion. So minus charge on sulfur is bigger in size, minus charge will be more diffused or more distributed or delocalized. Therefore this reaction in forward direction is more stable or is more favorable as compared to this reaction. Therefore basicity, or you will talk about the acidity, then H2S is greater than H2O as far as acidity is acidic character is concerned. So we are talking about the H2S reaction. H2S is a very foul smelling gas. H2S gas is a very foul smelling gas. H2S gas can act as a, you can say, reducing agent, because it can oxidize. It is in -2 oxidation state, so it can oxidize to an upper oxidation state and can reduce the other. So it is an H2S is an oxidizing state. Talking about the sulfur dioxide or SO2, the next would be sulfur dioxide. It can be paired by the reaction of H2SO4 with sulfur. H2SO4 concentrated H2SO4 when react with sulfur forms sulfur dioxide and with the H2O. So it is there. Now SO2 is an acidic in nature, because SO2 when dissolves in water gives H2SO3, that is sulfurous acid, which is acidic in nature. So SO2 is an acidic oxide. Now it can again act as a reducing agent also and oxidizing agent also, because it is an intermediate state, that is +4 oxidation state. So if there is a very strong oxidizing agent, so it can oxidize it to +4 to +6 oxidation state. However, most of the time it acts as a reducing agent, and it gets reduced from +4 to a less oxidation state and oxidizes other elements. So it has a reducing nature as well as oxidizing nature. So as far as it also shows some addition reaction, that SO2 when reacted with Cl2 forms SO2Cl2, that is sulfuryl chloride. And sulfuryl chloride is an reagent used in organic chemistry in sunlight, is an important reagent used in organic chemistry for the preparation of some of the for carrying out some of the reaction. SO2Cl2 is used, so it is sunlight reacts with Cl2 forms sulfuryl chloride. It can act as an oxidizing agent, it can act as a reducing agent also, it has a bleaching action also, because SO2 when hydrolyzed, H2O when hydrolyzed, it forms H2SO4, 2 moles of H2O and 2H. So this hydrogen acts as a reducing agent. This, because of this hydrogen, it has a bleaching action. But because the bleaching action is because of the reducing nature, therefore this is temporary. This bleaching action is temporary, it is not permanent. For ozone it was permanent because it was because of the nascent oxygen. However, it is because of the hydrogen, therefore the bleaching action would be temporary, and when again it comes in contact with oxygen, it will, you can say, oxidize and the bleaching action will be removed. So bleaching action here it is temporary. So this was SO2. Next, talking about the SO3. SO3 again is an anhydride of H2SO4. SO3, when aqueous solution of SO3 is very acidic in nature and forms H2SO4, that is sulfuric acid. SO3 is, you can say, 3 plus 0, that is sp2, planar in shape, trigonal planar in shape, hybridization of SO3, and it is an acidic in nature. It is a highly oxidizing in nature because sulfur here is in +6 oxidation state, that is highest oxidation state, so it cannot act as a reducing agent, but it can act as an oxidizing agent, and in fact it is a very strong oxidizing agent. So SO3 in water forms sulfuric acid, but if SO3 is in excess, then it reacts with water to form, first it forms H2SO4, and this H2SO4 again reacts with SO3 and forms H2S2O7, also known as oleum. And you will be familiar with the structure. It has an SO-S linkage, and the oxidation state of the sulfur here is, of both the sulfur, is +6. So this was about the oxides of sulfur. Now talking about the oxyacids of sulfur. Oxyacids, there are various oxyacids of sulfur. Kerose acid, that is sulfuric acid, and apart from sulfuric acid and sulfurous acid, there is kerose acid, that is H2SO5, Marshall's acid, that is H2S2O8, and oleum is there, H2S2. So O7, their structures are very important. They have been asked before, and because they show very peculiar structure are there. One is H2S2O3. Again, it has an exceptional structure which I talked about earlier in chemical bonding also. So first talking about the H2SO4. So H2SO4 is produced by the contact process. So industrial preparation is of H2SO4 is done by the contact process. It is done in 3 or 4 steps. So first, the SO2 reacts with the oxygen in presence of vanadium pentaoxide as the reagent. So SO2 reacts with oxygen, 2 moles of oxygen forms 2 moles of SO3, V2O5 is there. So this reaction is exothermic and reversible, and the forward reaction, you can say that this is a gaseous molecule. There are 3 gaseous molecules on the reactant side, and there are only 2 gaseous molecules in the product side. So there is a decrease in volume. So this reaction will be favored in the forward direction if pressure is high and temperature is low, because we know by the gaseous law PV equals to nRT. If you are by the ideal gas, so if pressure would be high, volume will be low, and if temperature will be low, volume will be low. So in this case, greater pressure and less temperature would favor the forward direction. However, temperature should not be much low, because when we are predicting this nature, we are taking into account only the thermodynamics and not the kinetics. So if temperature is very low, the rate of the reaction can be very less. So the temperature should be mediocre, taking in mind the volume concentration and also the rate concentration, that is both thermodynamics and kinetics. So temperature should be little bit low, but pressure should be very high. So this is the first reaction. Then SO3 reacts with the H2SO4. You use H2SO4 in between also to produce oleum, H2S2O7. H2S2O7, this is the reaction which we have discussed. H2SO4 is industrially produced by contact reaction. H2SO4 is highly acidic in nature, and its Ka1 is larger than 10. So Ka1 larger than 10 would mean it is very acidic in nature. The first deprotonation is very acidic in nature. and it acts as an H2SO4. Concentrated H2SO4 acts as a very powerful oxidizing agent. We have seen the effect of H2SO4 when it is dilute, when it is concentrated, the reaction of H2SO4 when it is very dilute, when it is dilute, and when it is concentrated with the metals and with the non-metals also. So keeping in that mind, the reaction of H2SO4 is placed. The next is sodium thiosulfate, that is Na2H2O3 dot 5H2O. It is produced by the reaction of Na2SO3 with the reaction of sulfur. In the absence of air will give you Na2H2O3. Na2H2O3. So its structure is very peculiar. There is a S double bond S, double bond O, and O minus, O minus. So this is the structure. So it is in -2 oxidation state, it is in +6 oxidation state. Average oxidation state is +2, but one sulfur is in -2 oxidation state, one sulfur is in +6 oxidation state. So this is the reaction, or this is the preparation reaction for sodium thiosulfate. Okay, so it can use as an anti-chlor. It can remove the chlorine from the surface of fiber, so it can be used as anti-chlor. These properties can be asked in the, you can say, as the columns, or it can be asked in the board exam directly, but as far as competitive exams are concerned, it can be asked as the column, that you will given be anti-chlor, which of the following compounds are used in anti-chlor, and there would be Na2H2O3 on one side. So this is how it can be used. Their reaction with silver salts, H2H2O3 is famous with its reaction with silver salt. So H2H2O3 reacts with Ag to form Ag2H2O3, which is white in color, and hydrolysis of Ag2H2O3 forms Ag2S sulfur sulfide, which is black in color. So this is how it is formed. However, if excess of H2H2O3 is formed, then it forms a soluble complex AgH2O3 2,3 minus, and this is also known as the hyporeaction, or it is used in the photography solution. Hypo solution also important reaction. So this was sodium thiosulfate. Sodium thiosulfate. One more thing about the sodium thiosulfate, few more reactions about sodium thiosulfate. That sodium thiosulfate, when it is heated to 215 degrees centigrade, it loses its 5 moles of water of crystallization, and when it is heated to 220 degrees centigrade, it decomposes to form a very peculiar structure of Na2S5 and Na2SO4. Important reaction, that is Na2S2O3 dot 5H2O, when heated to 215 degrees centigrade, 215 degrees, loses all its water molecules and forms Na2S2O3 anhydrous sodium thiosulfate, and when it is heated to 220 degrees centigrade, it forms Na2SO3 plus, or Na2SO4 plus Na2S5. So important reaction, because very peculiar reaction of Na2H2O3. So this was all about the chemistry of group 16 elements. Selenium, tellurium and polonium are not that important. There are not many compounds of selenium, tellurium and polonium. Mostly we are discussing only about, as far as group 16 is concerned, compounds of oxygen and sulfur are important. So this was all about the group 16 family. Now, and group 16 also, again, one thing is they are also known as chalcogens. So if somewhere it is mentioned about the chalcogens, so you should keep in mind that it is talking about the group 16 chalcogens. So now moving to the next group, that is group number 17, that would be of halogens. Group number 17, and the second last group number 17, halogens. So it has fluorine, chlorine, bromine, iodine, and rest is not as important. So it is fluorine, chlorine, bromine, iodine, and also known as halogens. It has an electronic configuration of NS2 NP5, very high electron enthalpy, very high ionization energy also. As far as the electron gain enthalpy is concerned, the electron gain enthalpy of Cl is greater than fluorine. Same was also the case in the sulfur and oxygen also. To remind, this is an anomaly because of the small size of fluorine and oxygen. There is much repulsion, and because of that, the much repulsion faced by the incoming electron. Therefore, the electron gain enthalpy of fluorine is less than chlorine, electron gain enthalpy of oxygen is less than that of the sulfur. However, the other group are the same down, the group atomic radii increases, ionization enthalpy decreases, electron gain enthalpy, I told you there is an anomaly, electronegativity decreases. As far as physical properties are concerned, these both are gases. Bromine is a liquid and iodine is a gas. Remind you, bromine is a liquid. This is an important thing. As far as bond strength is concerned, bond strength is F2 is very less because of the repulsion of the electrons. Therefore, bond strength order is Cl2 is greater than Br2 is greater than F2 is greater than I2. This is the absolute bond order reaction. If you were to talk about the reaction, then it would be F2. You can comment about something like this, that Cl2 Br2 I2, but the exact position is determined by the experimentally that F2 also has the bond length or bond order, I should say bond strength less than that of the Br2. So very peculiar thing that F2 has the bond length also less, because it is said that if bond length is less, then bond strength would be greater, but in this case F2 has the least bond length, and also F2 has the less bond length than as compared to Cl2, and also the bond strength of F2 is less than as compared to that of the Cl2. So this was all about the physical properties of halogens, and talking now about the chemical properties. So except of fluorine can only show +1, -1 and 0 oxidation state. Other halogen can show +1, +3, +5 and +7 oxidation state also, because of the presence of vacant d orbitals. So talking about their hydration energy of fluorine is the maximum because of its small size. Its hydration would be maximum, then chlorine, then bromine, and then the hydration energy of iodine would be least. So talking about now fluorine, F2. So F, as I have told you earlier, is the most electronegative atom. It has an electronegativity of 4, which is on the absolute, or on the Pauling scale it is the maximum. So it can be produced by the electrolysis of CaF2. So CaF2, when reacted with H2SO4, forms CaSO4 plus HF, and now this HF is reacted with Kf. This HF on reaction with Kf forms KHF2, and this on electrolysis gives H2 and F2. So this is the whole process for the preparation of fluorine gas. First, fluorspar CF2 is also known as fluorspar. Fluorspar is acidified with H2SO4, which forms HF. HF, when potassium fluoride is added to HF, it forms KHF2, and which on electrolysis forms H2 plus F2. This is how F2 is formed, or F2 is prepared. Now it is not possible to prepare fluorine by electrolysis of aqueous solution of NaF or KF, because when we are talking about the aqueous solution, if we are considering about the SRP, that is standard reduction potential, standard oxidation potential, then H2O when goes into half O2 plus 2H plus 2 electron, this has the standard oxidation potential of 1.23 volt, minus of 1.23 volt, and F minus going to half of F2 plus electron has an standard oxidation potential of minus 2.87 volt. So in case of aqueous solution of NaF or KF, H2O will be, since its SOP is more than the SOP of F minus, so this will be released in fact in place of F minus. Therefore this is not done, it cannot be produced by the you can say the electrolysis of aqueous solution of NaF or KF. You will learn more about the standard oxidation potential and standard reduction potential in electrochemistry. Yeah. So this was about the now oxidizing character. Talking about the oxidizing character of F2, we can say that we know that the F2 can have only fluorine can have only two oxidation state, 0 and -1 oxidation state. So since F2 is in 0 oxidation state, so it can only act as an oxidizing agent and gets itself reduced to -1 oxidation state. So its reactions with H2S reacts with F2 to form SF6 plus 2HF. So this one, and its reaction with SiO2 is very important because it attacks glass and forms SiF4. So this was about the F2. F2 is now talking about the Cl2. Cl2 is a greenish, you can say greenish yellow in color. Greenish yellow in color. So chlorine is a greenish yellow colored colorful gas. So now talking about chlorine, Cl2. Yeah. So chlorine is prepared by heating chloride with concentrated H2SO4 in presence of MnO2. MnO2, Mn is in +4 oxidation state, so it can act as an oxidizing as well as reducing agent. In this case, it is acting as an oxidizing agent. So what happens that it is, you have the H2SO4, so it is, I am just writing the ionic equation, MnO2 is also there, and then Cl2, so it is by heating the chloride, so it will be Cl minus ion will be there in the fan. So when it is heated, it gives us Cl2 Mn plus 2, and you can balance the oxygen, that is 2H2O here. So this is the reaction. In this case, the chlorine is produced by this reaction. So manufacture of chlorine is again done by the electrolysis process, also electrolytic process, electrolysis of NaCl or brine solution, concentrated NaCl solution. In this case, chlorine is liberated at anode, and it is obtained as a byproduct in many chemical industries such as manufacturing of sodium hydroxide. So in case of NaX, that is NaCl aqueous, and when electrolysis is done, so chlorine gas is evolved at anode, that is, you can say negative positive electrode. So Cl2 is existent positive. Now Cl2 has an oxidizing as well as the bleaching properties, both properties. Cl2, when it is act as an oxidizing agent, Cl from 0 oxidation state get reduced to -1 oxidation state, because its lowest oxidation state can only be -1, however its highest oxidation state can be +7. Now it also shows the bleaching actions, because when Cl2 reacts with the water H2O, then it forms HOCl, the HCl, 2 moles of HCl, and that is O, that is, you can say, nascent oxygen. Because of this, the nascent oxygen, it acts as a bleaching agent, and this bleaching action would be permanent because it is because of the nascent oxygen. However, if it would be have been of the hydrogen, as in case of SO2, then it would be a temporary bleaching action. However, in this case it is a permanent bleaching action, and it can act as an oxidizing as well as reducing character. So it oxidizes Br minus to Br bromine and I minus ion to iodide. There are many equations or many reactions, just you have to keep in mind. You will be given reactants and you have to predict the products, so you just have to keep in mind what are the properties of this given. Let's say if you are given a reaction in which Cl2 is in here direction, so you just have to keep in mind that it can act as an oxidizing agent, because it is an oxidizing agent, or it can act as a bleaching agent. You just have to keep this the mind in the properties, and you have to predict the corresponding, you can say, products. So as I have told you, bleaching action of SO3 is temporary because it takes place through reduction. However, it is oxidation because it takes place through oxidation. Now Cl2, the reaction with NaOH, we have talked about the reaction of NaOH with Cl2 in the S block elements also, but I will again talk it about here because it is an important reaction. Because the reaction of Cl2 with NaOH, if NaOH is dilute, then the products formed will be Cl minus, or you can say NaCl and NaOCl, that is disproportionate reaction in which Cl from 0 oxidation state goes to -1 and +1 oxidation state. However, if the NaOH used here is in place of dilute, it is concentrated. If NaOH used is concentrated, then the reaction would be NaCl and the products would be NaCl and NaClO3, that is Cl is in -1 and +5 oxidation state. So this is an important reaction. The same reaction is also shown with bromine and iodine also. So an important reaction or disproportionate reaction of chlorine with NaOH. So chlorine again reacts with CaOH, calcium hydroxide also, and forms CaOCl whole twice, that is bleaching powder, CaOCl, this is bleaching powder, also known as bleaching powder. So these are the few reactions of chlorine. Now talking about moving on to bromine. So let's talk about the bromine. So bromine is again is not a colorless gas, it is a colorful, it has a color also. Bromine as a, if in liquid, is in liquid form, found in the liquid form, bromine. So let's talk about Br2, that is bromine. Okay. So as far as its preparation is concerned, its preparation is same as that of the chlorine gas, that it is reacted with H2SO4. In the presence of H2SO4 reacted with MnO2, it gets oxidized to Br minus, get oxidized to Br2, and MnO2 reduced to Mn plus 2. The same is applied for bromine also. From seawater, the second is from seawater, that NaCl is the main component, but NaBr is also present there. So Br minus and Cl2. So as I have told you that Cl2 acts as an oxidizing agent, it oxidizes Br minus to bromine and Cl minus forms. This is again a preparation step for bromine gas. Again, it is a reddish brown liquid, as I told you earlier that it is not a colorless gas, it is a reddish brown liquid, it is formed in liquid state. Now this was all about the bromine. It is not much, there are not much properties, or much of the properties of bromine and chlorine are similar to each other. Bromine is volatile. Again, its reaction with NaOH, it shows the disproportionate reaction, but depending on the concentration and the dilute and concentrated NaOH, the you can say the products are defined. So the same reaction with this only, the most of the reaction of chlorine and bromine are the same. However, the bromine does not act as an oxidizing agent as the chlorine acts. So next is iodine, that is I2. Iodine is a violet color gas. So its preparation is same as that of the bromine also, that it is in presence of H2SO4 and MnO2 is used. So Mn is get reduced to Mn plus 2, and I from I minus get oxidized to I2. So this is the reaction for the preparation of I2. Yeah, it is a dark violet solid, undergoes sublimation, least soluble in water but much more soluble in Ki due to formation of Ki3. It is an important reaction that in water I2 is less soluble. In I2, if you treat in water, not much soluble, that is less soluble. However, if Ki, it is solubility in Ki is concerned, that is very soluble because of the formation of the compound Ki3, because formation of compound Ki3. Here I3 exists in I3 minus, it is an sp3d hybridization, 2 bond pair, 3 lone pair, stake number 5, sp3 hybridization. All the 3 lone pair are equatorial position, 2 iodine at axial position. So therefore its you can say geometry is linear. So sp3 hybridization. This is reaction with NH3. Now considering its reaction with NH3, so NH3 when reacts with iodine, NH3 in gaseous state reacts with iodine, shows no reaction. No reaction takes place. However, if aqueous solution of NH3 is taken, that is NH4OH. So if aqueous solution NH4OH, or you can say NH3 again, or NH4OH, whatever, NH3 is reacted with iodine, then it forms an explosive compound Ni3NH3, Ni3 dot NH3 plus Hi. So this is an explosive compound, very explosive compound. So the reaction, these types of reactions are important because but slightly changing the conditions, the reaction the products or the reactions differ. Therefore these you have to keep in mind these type of reactions, because this type of reaction can be asked in any competitive exams. So NH3 when it is in gaseous form does not react with iodine, but however when NH3 is in aqueous form, it reacts with iodine and forms Ni3.NH3, which is an explosive compound. Its reaction, one of the important reaction of iodine is with hyposolution. Hyposolution is S2O3 2 minus. It reacts with I2 and or it is a thiosulfate ion. It forms S4O6 4 minus or 2 minus tetrathionate ions plus 2I minus. This is used in the iodimetric titration, which is carried out the estimation of iodine using the starch solution. So it is used for the estimation of iodine using starch solution. So this reaction is very important and it is used for hyposolution reaction. This is tetrathionate ion and this is thiosulfate ion. So this was about all the iodine I2. Now talking about their acids, halogen acid, that is HCl, HBr, Hi and HF. So first talking about the first compound that we are talking about, I will be talking about them simultaneously because HCl, HBr and Hi have quite the properties that are similar to all the three. So first would be the preparation of these. So they are directly prepared by the combination of element, that is H2 plus Cl2 gives HCl, Br2 gives HBr and H2 plus you can say iodine gives Hi. However, these are photolytic reaction, that is in presence of light and in the presence of Pt as an you can say Pt H2 plus X2 give 2HX, Pt as a catalyst, X can be Cl, Br and I, can be any of these three. So this was one of the reaction of this. Now the properties. When three parts of first we are talking about the properties of HCl. So when three parts of concentrated HCl and one part of concentrated HNO3 are mixed, it acts as a very good you can say mixing agent for dissolving noble gases, inert noble gases, something like inert noble metals, something let's say gold and platinum. So three parts of concentrated HCl and one part of concentrated HNO3, it can dissolve. So let's say talking about the gold. So gold plus Au plus 4H plus NO3 minus plus 4Cl minus, it forms a complex AuCl4 minus, which is a soluble complex. So it dissolves AuCl4 minus. So it dissolves this AuCl4 minus is a soluble complex. So it dissolves the compound Au. So here three parts of HCl and one part of HNO3. This is the mixture used for dissolving HNO3 for dissolving Au or platinum or other inert metals or noble metals. Now talking about the reducing property and stability of hydra acids. Now HCl is quite stable. Now Cl is here is minus 1 oxidation state, so it can oxidize, though it acts as a reducing agent in such cases. So it can be oxidized by a strong oxidizing agent like Pb3O4. I have told you earlier that Pb in +4 oxidation state is very stable. Now Pb3O4 is a mixed oxide of PbO plus PbO2, where there are 2:1 ratio of PbO to PbO2. So 2:1 ratio of PbO to PbO2. So it acts as an oxidizing agent. Pb3O4, Pb2O2, MnO2, Mn, you can say Mn +7 oxidation state, MnO4 minus, and K2Cr2O7. These all are very strong oxidizing agent. This oxidizes Cl minus to chlorine, that is from 0 to 1 oxidation state. HBr, talking about HBr is not very stable. So stability is showing that stability of, if you will talk about the stability, then HCl, HF is the most stable hydride, then HCl, then HBr, then HI. So this is the stability order, stability of hydrides. HF greater than HCl, greater than HBr, greater than HI. This is stable of hydrides and acids. HI is the least stable hydrogen halide. HBr, the properties of HBr are quite similar to that of the HCl, and HI are also quite similar to that of that. But because the stability of this is the minimum, therefore it acts as the strongest reducing agent. It can lose its H plus, it can provide H plus quite easily, therefore it is the strongest reducing agent and it is the weakest reducing agent. Now detection of cation. HCl, HBr and HI are used for the detection of cation because they are you can say their salts are very colored. They form colored salts with many cations. For example, Ag. So AgNO3 reacts with HCl to form AgCl, which is a white precipitate. In case if it is Hi, then it will form AgI, which is a yellow precipitate. If it is you can say HBr, then it will form AgBr, which is a pale yellowy precipitate. So it forms colored precipitate with this. Therefore, it is used in the detection of cation. The same reaction takes place with, you can say, lead acetate also and mercury nitrate also. That this combination which I talked about, this three parts of HCl plus one part of HNO3 is also known as aqua regia. So if it is mentioned somewhere directly in any question, so if it is aqua regia mentioned, you should know that it means that 3 parts of HCl and one, it is talking about 3 parts of HCl and 1 part of HNO3. Besides of other properties, it can also show the other properties, that it can act as an very, it is a very you can say it can act as an oxidizing agent also, it is a very acidic mixture, but besides of this, it has a special property that it can dissolve the inert in noble metals also. Now talking about the hydrofluoric acid or HF, we are talking about the hydrofluoric acid separate from the other acid, that is HCl, HBr, HI, because HF shows some properties which are not shown by the HCl, HBr, or HI, or HF possess some properties or possess some property different from the other you can say acids. So hydrofluoric acid H2 and F2 combine with each other violently even in dark to form HF. So it is a very exothermic reaction exothermic reaction between hydrogen and fluorine. So therefore it is not a good method of preparation for HF. Therefore anhydrous HF is obtained by heating dry potassium hydrogen fluoride, that is KHF2. If you heat KHF2 in a copper retort, then it will form Kf plus HF. So this is used as a preparation method for HF. HF shows the hydrogen bonding, and therefore in aqueous solution you can say in aqueous solution it I have talked about this chemical bonding also, that it is something like this. It forms an angle of 120 degree. So this is this angle is 120 degree. So it shows the hydrogen bonding, therefore it acts as even weak acid in the aqueous solution. Because of this hydrogen bonding, it is not very easy to remove that hydrogen atom from this. Yeah, so this was about the HF, some property of HF. It can also be produced by fluorospar. So fluorospar when reacted with H2SO4 form CaSO4 plus 2 moles of HF. Now the important property is that aqueous HF acts as corrosive, therefore when it's reacted with silica or in glass it acts as a corrosive. So when Na2SiO3 reacts with HF, it forms Na2SiF6. So therefore it acts as an corrosive because it reacts with the glass and corrode it. So this is one of the properties. Now HF reacts with CCl4 to form freons. It is an important property that CCl4, one thing to notice that CCl4, SiCl4, GCl, all the other tetrachlorides undergo hydrolysis. However, CCl4 doesn't undergo hydrolysis because it has no vacant d orbitals in which the nucleophile can attack, I should say Lewis base can attack. So CCl4 plus HF reacts and forms CFCl3 plus HCl. So these are also known as freons in which there is carbon and there is, you can say, Am, or you can say FCl3 or F2Cl2 or F3Cl. This type of combination is known as the freons. So this was all about the acids. Now we'll talk about the oxides of chlorine. So first oxide of chlorine would be Cl2O, that is chlorine dioxide, ClO2, sorry, chlorine dioxide. ClO2, you can ClO2, so two bond pair, and it is a, I think, odd electron species, yeah, odd electron species, ClO2. So its preparation, let's look at the preparation step of it. It can be prepared by reaction of potassium chlorate and oxalic acid, that is KClO3 plus H2C2O4, that is oxalic acid. When they are reacted or heated to 90 degrees centigrade, it forms ClO2 plus CO2 plus K2C2O4 plus H2O. This is an, I think, a redox reaction because C from +3 oxidation state is going to +4 oxidation state. Chlorine from +5 to is going to +4. So here it is reduction, there is oxidation. So it is a redox reaction. You can easily balance the reaction. So this was the preparation step for the ClO2. yellow gas at room temperature dissolves in water. This is a, you can say, yellow gas. Its colored is yellow gas. So it dissolves in water and gives a green solution. So ClO2 when dissolves in water gives dark green solution. At room temperature dissolves in water and gives the green solution. In light you can say it is ClO plus evolves oxygen, so it is a nascent oxygen, so it acts as an oxidizing agent as well as a bleaching action. It has a bleaching action as well as act as an oxidizing agent. ClO2 dissolves in NaOH forming chlorite in chlorate, that is ClO2 is an anhydrous oxide of HClO3 and HClO2. So it is an important point to be noted that HClO3 and HClO2, chlorite and chlorate, ClO2. Now Cl2O6 is a mixed anhydride of HClO4 and HClO3, because on dissolving in water it gives a mixture of these two acids. In solid state Cl2O6 exists as ClO2 plus and ClO4 minus. So ClO2 plus will mean 2 plus 2. So 2 bond pair, 2 lone pair, sp3 hybridization, bent or V-shaped, and here it is 4 bond pair and 2 lone pair. So sp3d2 hybridization and square planar in structure. So 4 bond pair and 2 lone pair. This was it. Yeah. So this was all about the properties of ClO2. It can act as an oxidizing agent. It has a bleaching action also. So if you are given and you can say if in HI with react with ClO2, let's say HI the reaction with ClO2, so HI will be easily get oxidized and it will get reduced. These are few reactions which you have to HI will get oxidized to I2. Most probably if there is a negative oxidation state, it go oxidizes to 0. This is a common, or I will not say it is a generalization, but commonly observed thing is that if there is a non-metal which is in negative oxidation state, and if some you can say some is oxidizing agent is there which is not in excess, then it oxidizes it to the 0 oxidation state and gets itself reduced. Here it is gets reduced to Cl minus n. So this is a I will not say it is a generalization, but this is what I have observed most of the time this happens. Now talking about the next, that is dichlorine monoxide, which would be Cl2O. Cl2O is prepared by the reaction of chlorine with the HgO, which forms HgCl2.HgO and also forms correspondingly Cl2O. So this is all. Dichlorine monoxide is not that important oxide. Next is the bleaching powder or CaOCl2.H2O. So its preparation, we have talked about the preparation in S block elements lecture also, that CaOH whole twice, that calcium hydroxide when react with Cl2 gives CaOCl2 plus H2O. Originally this is CaOCl, that is, it is an you can say it is also known as chlorohypochlorite because it is a mixed salt of you can say hypochloric acid and hypochlorous acid, hydrochloric acid and hypochloric acid, because it is mixed oxide of HOCl and HCl mixed oxide. So hypochloric acid and hypochlorous acid and hydrochloric acid. So it is a mixed compound. It is a pale yellow powder. It has a bleaching action which we have talked about in S block elements also, so it is not need to repeat it again. So next topic is the oxy acids of halogens. So we have talked about the simple HF, HBr, and now we will talk about the oxy acids of halogen. First would be HOX series, that is hypofluorous acid, HOF. Talking about the HOF, so HOF has been prepared by trapping F2 and H2O. So if F2 is reacted with H2O in presence of light, then it forms HOF. It is an unstable quantity, but HOCl, HOBr and HOI are not very stable and known only in aqueous solution. Now talking about the hypochlorous acid. So hypochlorous acid is a weak acid, HOCl is a weak acid, HOBr and HOI are also weak acids simultaneously. Most of the properties of HOCl, HOBr and HOI would be same, and HOF, the oxyfluoric acid of fluorine will be different and of the other Cl, Br and I would be relatively different in this case. Now talking about the HXO2 series, that is HClO2. So HClO2 here, Cl is in plus 3 oxidation state, its structure would be Cl double bond O, O minus, and it will have 1 and 2 lone pair. So Cl plus 3 ClO2 minus, it would be something like this. So 2 bond pair, 2 lone pair, 2 bond pair, 2 lone pair, sp3 hybridization, bent or V-shaped, so to say, V-shaped structure. So this is HClO2. Its preparation, there are some preparation step of HCl2 and some properties, not very important property. It is in plus 3 oxidation state. The next is HClO3. HClO3 can act as an oxidizing agent as well as a reducing agent because it is in intermediate state. HClO3 plus 5 oxidation state, it can oxidize itself to plus 7 and also get reduced up to minus 1 oxidation state. So it can act as both oxidizing agent and both as a reducing agent. However, it will act as a reducing agent in case there is a very powerful oxidizing agent only. Now talking about the perchloric acid, that is HClO4. HClO4 is a very highly acidic acid. HClO4 is a most stable oxyacid of chlorine and the highly acidic acid, and its some properties are, it is one of the strongest acid and it dissolves most of the metals. It dissolves zinc also and forms zinc chlorate, and it also acts in here the chlorine is in plus 7 oxidation state, so its concentrated form acts as a very strong oxidizing agent because it can get reduced to up to the minus 1 oxidation state also. It oxidizes sp2O5 and form HPO3. So let's talk about some of the order. That if you talk about the acid strength, the HI, HBr, HCl and HF, then HI is the most acidic in character, then HBr, then HCl and then HF, because of the, you can just look at the corresponding ionization reaction and look at the stability of the anion. I minus is most stable because of the large size of the I, the minus will be more diffuse. So I minus more stable than Br minus, then Cl minus, then F minus. Therefore HI would be most acidic and HF would be least acidic. Now talking about the pseudo halogens are consisting of 2 or more atoms, of which one of is nitrogen and other behave like halogen. Therefore they are known as pseudo halogen compounds. For example, Cn whole twice acts as an SCN whole twice. All these category comes into the pseudo halogen compound. So some of the questions have been, one of the questions have been asked in the previous years in the JEE, I think very far, about 10 or 15 years ago. 4 options were given and you were asked which one of them is a pseudo halogen. So just about that, nothing much have been asked on this in the previous years. Yeah. Now this was all about the group 17. Now moving on to group 18, that is the group of the inert gases. So there is not much compounds of the noble gases. However, the xenon, there are some compounds of the xenon with fluorine and oxygen. It is found to be xenon is found to be most reactive among the noble gases. So talking about the group 18, it is helium, neon, argon, krypton, I think radon or xenon, something, I don't remember completely, but I think xenon and then it's radon. I think this is the order, and it has the configuration of NS2NP6. Their atomic radii, they are the most large in their respective period. NS2NP6, complete octet, very not very reactive, in fact very least reactive. Now one important thing would be clathrate compound. Inert gas molecule get trapped in the cages formed by the crystal structure of water. Water forms a crystal structure, and these you can say noble gases get trapped in the compounds. So because of this, there is a, I think, approximate reaction would be corresponding to each 6 water molecules there is one inert gas molecule. So corresponding to 6 water gas molecules there is one inert gas molecule, and all such compounds are known as clathrate compounds. I should add here clathrate compounds. They are known as clathrate compound. Now talking about the compounds of the group 18 family, so I will just drop itself to xenon because there are no compounds of helium, neon, argon and krypton to be found, so it's directly to xenon. So the most important reaction for the as far as the xenon is concerned is hydrolysis of xenon. Xenon reacts with oxygen and fluorine most of the time. So xenon, when reacts with F2, XeF2, on reaction on hydrolysis of it, will give the xenon, and corresponding to it will be HF, and O2 is produced. This is a slow reaction. However, if you want to do hydrolysis, fast hydrolysis, then do it with alkali. If in place NaOH is used, then xenon plus O2 plus NaF is used. NaF plus H2O is also produced, and this reaction is fast as compared to the first reaction. So if you want to do fast hydrolysis, do it with alkalis, and with a simple water hydrolysis, it is a slow reaction. So there are few compounds, XeF4, XeF6 and XeF2. So talking about their hybridization, so XeF2 would be 2 bond pair plus 3 lone pair, it's like number 5, sp3d hybridization, linear in shape. XeF4, 4 plus 2, bond order stack number 6, so hybridization sp3d2, 4 plus 2, 2 lone pairs, both reside in, there is no axial position in this, so it is square planar in shape. XeF6, 6 bond pair, 1 lone pair, so pentagonal pyramidal, stack number 7, sp3d3. Here d orbitals involved are dx square, dyz and dxz, and here d orbitals involved are dz square, dx square minus y square, and in this the d orbital involved is dz square. So these are few of the important things, and I think that this reacts with MF, you can say the metal F, to form XeF7 minus and M plus. So this is a reaction which you have to keep in mind, that it reacts with F minus quite easily and forms corresponding reactions. Now talking about the order of oxidizing power. Oxidizing power in xenon F, it has plus 2 oxidation state, it has plus 4, it has plus 6. So oxidizing state of this would be more, because plus 2 can get oxidized to more than plus 4 and then plus 6. So oxidizing power would be XeF2 greater than XeF4, which is greater than XeF6. So this is the oxidizing power order. Now talking about the xenon oxygen compounds and hydrolysis, so the most important part of the group 18 would be considering the hydrolysis of xenon oxygen fluoride compounds, or I should say xenon fluoride compounds. So hydrolysis of XeF4 and XeF6 with water gives XeO3, that is XeF4 when react with H2O gives xenon plus XeO3. So you can say it is a disproportionate reaction. Xenon from plus 4 oxidation state is going to 0 oxidation state and plus 6 oxidation state. Along with it, HF and oxygen is also produced. So oxygen also is getting involved in this, because oxygen from minus 2 oxidation state is going to 0 oxidation state. So there are two atoms which are getting oxidized and one atom which is getting reduced. Talking about XeF6, hydrolysis of XeF6, in this case only XeO3 is formed and corresponding to it HF is formed. So in this case this is not no redox reaction, this is a redox reaction, however this is no redox reaction, it is just a simple hydrolysis, no change in oxidation state in the reactant and in product side. This is a complete hydrolysis. But if you want to do in partial hydrolysis, for example, let us consider the partial hydrolysis of XeF6. Then partial hydrolysis of XeF6, mind you, these reactions are not balanced, but again you can balance them quite easily if you know the concepts of redox reaction quite well. Just equal the electrons that one species being reduced and one species being oxidized, and you will easily can balance this reaction. So XeF6 plus H2O, if we are considering partial hydrolysis, so in this case I just said 3H2 because I have to say a difference between this. So partial hydrolysis gives XeOF4, so it is an oxygen, fluorine and xenon compound. Here it is 5 plus 1, so it has sp3d2 hybridization with its shape being the square pyramidal, 5 bond pair, 1 lone pair plus HF. Now it is one molecule. If there are two molecules of H2O, then it forms Xe O2 F2. It would be 4 plus 1, so it would be sp3d hybridization with the shape being with the shape of this would be T shape, because the lone pair will acquire the equatorial position, so it will be T shape XeO2F2 plus HF. So this is the some of the hydrolysis compounds formed. This is an important reaction which can be asked in competitive exams and in board exams also, that this is about the partial hydrolysis. This is according to partial hydrolysis, and above given is according to, this is complete hydrolysis, this is also complete hydrolysis. One thing to note, that the complete hydrolysis of XeF4 is a disproportionate reaction. However, the reactions that partial hydrolysis and even complete hydrolysis of XeF6 is not a disproportionate reaction. So I think this is all for the group 18 elements, because there are very less reactive, so not much of the properties are there for group 18 elements. So I have taken into, so we have studied each of the group from group 13 to group 18. Group 13 is boron family, group 14 is carbon family, group 15 is nitrogen family, group 16 is oxygen family, also known as chalcogens, group 17 is halogens or fluorine family, and group 18 is helium family, or you can say noble gases. So we have studied the properties of each of the groups in detail, and I have covered all the portion, all the things which are required. Now I will solve more questions in I have solved questions in the advanced lecture of advanced module of P block elements, so you will get a feel of the subject, that what type of questions have been asked in JEE, and what type of JEE and CRT, and what type of questions can come in the have come in the previous years and can come in the upcoming years. So one thing is to be noted, to be sure, that theory of the inorganic chemistry is very vast, but as long as you are not solving questions, you are not going to learn about the inorganic chemistry, because many of the concepts are cleared when you are starting to solve the questions. So I will solve ample amount of questions in advanced lecture of P block elements, so you would get a good feel of how the questions are being made out of P block elements. So I hope that you enjoyed the lecture, and if you have any problem regarding any topic, just rewind the tape and solve your confusion. So thank you.